Have you ever stopped to think about how our distant ancestors measured the passing of time without the sophisticated technology we take for granted today? Long before smartphones and digital clocks, ancient civilizations were tracking the movements of celestial bodies with astonishing precision, creating intricate devices that not only marked the hours and seasons, but often encoded profound astronomical knowledge that we are still unraveling centuries later. These remarkable inventions, born from a deep human desire to understand our place in the cosmos, stand as testaments to the ingenuity and perseverance of cultures across the globe, from the sun-drenched plains of Egypt to the misty highlands of Peru. They didn't just tell time, they wove together science, spirituality, and art in ways that continue to leave modern researchers in awe, challenging our assumptions about what ancient societies were truly capable of achieving. Throughout human history, the measurement of time has been far more than a practical necessity. It has been a profound expression of our relationship with the universe itself. These ancient timekeeping devices, many of which remain shrouded in mystery, represent some of humanity's earliest attempts to capture the rhythm of the heavens and translate it into something tangible and meaningful here on Earth. We're about to embark on a captivating journey through 30 of the most enigmatic and fascinating timekeeping artifacts ever discovered, each with its own story to tell and secrets to reveal. From celestial calendars carved into stone to intricate mechanical wonders that seem almost out of place in their historical context, these devices not only tracked days and years, but often served as portals to understanding the beliefs, priorities, and cosmic perspectives of the people who created them. As we explore these extraordinary creations together, you'll discover how something as seemingly simple as tracking time could involve such breathtaking complexity and innovation. These aren't just relics gathering dust in museums, they are windows into the minds of ancient astronomers, engineers, and philosophers who gazed at the same stars we see today and asked questions we are still trying to answer. You'll encounter mechanisms that predicted eclipses with pinpoint accuracy, structures aligned with solstices and equinoxes, and portable sundials that traveled across empires. Some of these devices are so advanced that historians and archaeologists continue to debate how they were possibly made with the technology available at the time. So settle in and prepare to be amazed, because what you're about to witness will forever change how you think about time, history, and the incredible capabilities of our ancestors. Our journey into these ancient enigmas begins at the bottom of the sea, with a discovery so extraordinary it single-handedly rewrote the history of technology. In the year 1901, sponge divers exploring a Roman-era shipwreck near the Greek island of Antikythera stumbled upon a heavily corroded lump of bronze and wood. For decades, this unassuming object languished in a museum storage room, its true significance completely overlooked. It wasn't until the 1970s that advanced imaging technology, like gamma-ray and X-ray tomography, finally revealed the shocking truth hidden beneath 2 millennia of seabed encrustation. This was not a simple statue fragment or a piece of the ship's hardware. It was an incredibly sophisticated mechanical device, a labyrinthine clockwork of interlocking bronze gears of breathtaking precision. Dubbed the Antikythera Mechanism, it has since been recognized as the world's oldest known analog computer, a title that speaks volumes about the lost engineering prowess of the ancient world. The complexity of this 2,000-year-old device is nothing short of mind-boggling. Imagine a shoebox-sized wooden case operated by a hand crank on the side. Turning that crank would set in motion at least 30 precisely cut bronze gears, their teeth engaging with mathematical perfection to drive a series of at least 7 delicate pointers across multiple circular dials on both the front and back of the mechanism. These dials were not just for telling the hour, they were a miniature mechanical simulation of the cosmos itself. The front dial featured pointers for the sun and moon, showing their positions against the backdrop of the Egyptian zodiac and the Greek calendar. It even included a beautiful rotating black and white sphere to display the phases of the moon. But the true genius of the mechanism is revealed on its more complex backside, where a series of spiral dials acted as astronomical calendars, predicting with remarkable accuracy the timing of lunar and solar eclipses and tracking the irregular orbits of the 5 known planets. This leads us to the central, captivating mystery that has consumed researchers for decades. What was its ultimate purpose? Was it a sophisticated scientific instrument for astronomers, a sacred device for religious ceremony, or a tool for astrologers to cast horoscopes? The evidence points to a machine that brilliantly served all these functions at once, a testament to the intertwined nature of science and belief in the ancient Greek world. On one hand, its ability to predict eclipses and model planetary motion demonstrates a highly advanced understanding of celestial mechanics, far beyond what historians believed possible for that era. This was hard science. On the other hand, eclipses and planetary movements were also seen as powerful omens, messages from the gods that could influence the fate of kings and empires. The mechanism could have been used to determine the exact timing of important religious festivals or to identify astrologically significant moments for state decisions. It wasn't a matter of science versus superstition. For its creator, it was all part of a single, magnificent cosmic order that this incredible device helped to decipher and display. The Antikythera Mechanism stands as a powerful reminder that the human drive to understand the universe has always blended meticulous observation with a search for deeper meaning. While the Antikythera Mechanism showcases the mechanical genius of the ancient world, our next mystery takes us to a much earlier time and a far more monumental scale. We travel now to the windswept Salisbury Plain in England, to a site that has captivated the human imagination for millennia, the Great Stone Circle of Stonehenge. This iconic Neolithic monument, constructed in phases beginning over 5,000 years ago, is far more than a ring of imposing standing stones. For centuries, observers have theorized that its arrangement was not random, but deliberately designed to frame the movements of the sun and moon with a precision that seems almost supernatural for a people working with only primitive tools. The sheer ambition of its construction is staggering, but the potential astronomical knowledge encoded within its architecture is what truly cements its status as one of history's greatest timekeeping enigmas. The most famous and undeniable alignment is with the summer solstice. On the longest day of the year, the sun rises directly over the heel stone, a massive sarsen block set outside the main circle, and its rays shine straight into the heart of the monument, perfectly framed between the pillars of the Great Trilithon. This alignment is so precise that thousands of people still gather there every year to witness the event, but the astronomical significance likely goes much deeper. Some researchers propose that the entire configuration of 56 Aubrey holes pits circling the inside of the bank could have been used as a primitive astronomical computer, a way to predict lunar eclipses by moving markers around the circle to track the complex cycles of the moon. Other stones appear to align with the winter solstice sunrise and sunset, and even with the extreme positions of the moon during its major standstills, events that occur only every 18.6 years. This suggests the builders were not just noting annual solar events, but were engaged in a multi-generational project of celestial observation, patiently recording patterns in the sky across decades. This leads to the profound and haunting question: how did a prehistoric society achieve such precision? The construction itself is a marvel of Neolithic engineering. The larger sarsen stones, weighing up to 50 tons each, were quarried from sites over 20 miles away and then transported, likely on wooden sledges and rollers, to the plain. The smaller bluestones, which form the inner circle, have an even more incredible origin, hauled from the Preseli Hills in Wales, a journey of nearly 150 miles. The process of shaping these monstrous stones using only other harder rocks as hammers and then erecting them with techniques that likely involved ropes, levers, and immense frame timber structures, represents a staggering communal effort. But the intellectual challenge was even greater. To align the monument correctly, its architects needed an incredibly sophisticated understanding of geometry and a method for making accurate astronomical observations over long periods, passing this knowledge down orally through generations without a written language. They were master surveyors, astronomers, and engineers, their minds capable of conceptualizing and executing a project that would forever mark their relationship with the cosmos in the very landscape they inhabited. Ultimately, the true purpose of Stonehenge remains wrapped in layers of time, but its function as a celestial calendar is one of the most compelling theories. It was likely a place of immense ritual and spiritual significance, where the changing seasons and the cycles of the heavens were directly tied to the community's beliefs, agriculture, and identity. By marking the solstices and equinoxes, the builders created a permanent anchor point in their world, a way to predict the coming of winter or the planting of crops, and to perform ceremonies that ensured the sun would continue its journey and return each year. It stands as a testament to humanity's universal and ancient desire to find order in the cosmos, to measure the immeasurable flow of time, and to build something monumental that would echo that understanding for thousands of years to come. Leaving behind the misty moors of Britain, our exploration of ancient timekeeping now takes us to the hot, dry air of Upper Egypt, to the Temple of Hathor at Dendera. Here, chiseled into the stone ceiling of a chapel dedicated to the god Osiris, lies one of the most breathtaking and debated celestial maps ever created by an ancient civilization, the magnificent Dendera zodiac. This sprawling bas-relief is not a simple decoration. It is a complex and beautifully detailed snapshot of the night sky, frozen in time for over 2,000 years. Unlike the mechanical gears of Antikythera or the monumental stones of Stonehenge, the Dendera zodiac presents its astronomical knowledge as art, weaving together constellations, planets, and deities into a single, captivating masterpiece that continues to challenge our understanding of Egyptian science. Carved during the Ptolemaic period, likely around 50 B.C., the circular chart is a rich tapestry of symbols and figures. At its heart, you find the familiar constellations of the zodiac, but portrayed not as abstract patterns of stars, but as the vibrant gods, goddesses, and mythical creatures of Egyptian cosmology. A massive figure of the sky goddess Nut arches over the entire scene, representing the heavens themselves. The North Pole is clearly marked, and the 36 decans, star groups used to tell time through the night, encircle the outer edge. The 5 known planets are shown as deities holding staffs placed in their perceived positions. This incredible detail suggests the carving was far more than a symbolic representation. It was a precise and functional celestial map, a permanent record of the cosmos as the Egyptian priests observed and understood it. The sophistication of this map immediately raises a profound question. How did the priests of Dendera acquire such precise astronomical knowledge? The positions of the constellations and the apparent path of the sun, known as the ecliptic, are depicted with an accuracy that implies centuries of meticulous night sky observation. These priest astronomers would have worked without telescopes, relying solely on the naked eye and simple sighting instruments like the merkit, a forked stick used as a rudimentary transit to track the alignment of stars. They patiently recorded the slow wobble of the Earth's axis, known as precession, which causes the position of the constellations to shift over vast periods of 26,000 years. Some researchers have even attempted to date the zodiac by calculating the precise astronomical alignments shown, using the position of the vernal equinox among the constellations to pinpoint the exact era the map represents, whether it was an observation of their current sky or a record of a much older tradition passed down through generations. This leads directly to the central mystery surrounding the slab. What was its true purpose within the temple? One compelling theory is that it served as a sophisticated liturgical calendar, guiding the timing of religious festivals and ceremonies that were intrinsically tied to the cycles of the heavens. The rising of certain stars, like the heliacal rising of Sirius, which heralded the annual flooding of the Nile, was of critical importance to Egyptian life and religion. The map could have helped priests determine the exact right moment to begin these vital rituals. Another, more profound possibility is that the zodiac was a spiritual guide to the cosmos, a map of the soul's journey after death. The temple was dedicated to Osiris, the god of the afterlife, and the chapel housing the zodiac was part of a larger complex celebrating his resurrection. The constellations could have represented stages of this journey, with the sun god Ra's boat sailing through the celestial realm, offering the deceased pharaoh a divine roadmap to navigate the stars and achieve eternal life. It beautifully blurs the line between an astronomical tool and a theological text, carved in stone for eternity. Today, the original Dendera zodiac resides in the Louvre Museum in Paris, a controversial removal by 19th century explorers, while a replica remains in its original place on the ceiling. Its departure from Egypt, however, cannot remove the powerful questions it inspires. This single artifact forces us to reconsider the depth of ancient astronomy. It stands as a powerful testament to the human impulse to not only chart the heavens but to find our place within them, merging the measurable movements of planets and stars with a deep, spiritual search for meaning that resonates just as strongly today as it did 2 millennia ago under the Egyptian stars. Moving from the grand temples of Egypt, we venture even further back in time, to the very dawn of the Bronze Age, where a discovery in a German forest would present a mystery almost as old as civilization's first attempts to understand the sky. Our fourth mystery is the Nebra sky disk, a stunning artifact that utterly shattered previous assumptions about the astronomical sophistication of prehistoric Europe. Unlike the stone circles or temple carvings we've explored, this was a portable masterpiece, a solid bronze disc inlaid with gold symbols that seems to hold the very heavens in its hands. Its story reads like a thriller, not excavated by archaeologists but looted by treasure hunters in 1999 from a prehistoric site atop the Mittelberg Hill in Nebra, Germany. After a dramatic sting operation recovered it from the black market, experts were left astounded by what they held. This was not merely a decorative shield or ceremonial plate. It was the oldest known concrete depiction of cosmic phenomena anywhere in the world, dating back an astonishing 3,600 years. The imagery on the disc is both beautiful and instantly recognizable, yet its arrangement is deeply mysterious. Against a blue-green patinated bronze background, we see a cluster of 32 gold dots widely interpreted as stars. Among them, a large golden circle and a crescent moon shine prominently. Flanking the disc on opposite sides are 2 golden arcs, their curved edges hinting at a specific purpose. Perhaps most intriguing of all, a final addition was made to the artifact sometime after its initial creation. A third arc at the bottom, often called the sun boat, a graceful curve with radiating lines that looks like a vessel sailing through the sky. This layering of elements, added across potentially generations, suggests the disc was not a static object but a living tool, its meaning and function evolving alongside the community that cherished it. This very portability is at the heart of the debate over its true function. Was it a practical, working astronomical instrument? One compelling theory suggests the 2 opposing arcs along the sides represent the exact range between the sunrise and sunset points on the horizon as they shift between the summer and winter solstices. By aligning the disc with the local landscape, a knowledgeable user could have employed it as a simple yet effective device to measure the sun's changing path, crucial for marking the solstices themselves. This knowledge would have been the power to predict the changing seasons, to know when to plant and when to harvest, making the disc an incredibly valuable tool for agricultural timing and the survival of the entire community. It transforms from a pretty picture into a functional handheld calendar, Yet, its exquisite craftsmanship and use of gold, a material associated with the divine, point strongly toward a powerful religious or ritual purpose. The disc was found buried alongside 2 prized swords, 2 axes, and 2 spiral arm rings, a hoard of immense value that seems less like a toolkit and more like a votive offering to the gods. The sun boat ark is a potent symbol in Bronze Age iconography, representing the vessel that carried the sun across the sky by day and through the underworld by night. This suggests the disc could have been a central object in rituals led by a shaman or chieftain, a concrete representation of the cosmos used to demonstrate their unique connection to the celestial forces that govern their world. It may have been less about calculating dates and more about mediating between the earthly and the divine, a sacred object that explained the cosmos and humanity's place within it. The most captivating idea is that these functions were never separate to begin with. For the people of the Bronze Age, the practical and the spiritual were likely one and the same. The disc's ability to track the solstices would have been seen not as mere mechanics, but as a form of sacred knowledge. The person who could read the sky with this object held both temporal and spiritual authority, guiding the community's agricultural cycle while also performing the rituals that ensured the sun would continue its journey and return each spring. The Nebra sky disk, therefore, stands as a unique and powerful bridge between worlds. It is a functional instrument, a religious icon, and a communal calendar all fused into one, offering us a breathtaking glimpse into the mind of a people for whom understanding time was a sacred act, a way of weaving their lives into the very fabric of the cosmos. While Bronze Age Europeans looked to the heavens from their forested hills, an entirely separate civilization on the other side of the Atlantic was developing a system of timekeeping so advanced and precise that it rivals our own modern calendars. We now travel to the steamy jungles of Mesoamerica, to the world of the ancient Maya, whose obsession with time went far beyond marking seasons. They sought to map eternity itself. At the heart of their cosmic vision was a complex interlocking system of calendars, the most famous and enigmatic of which is the long count, a linear timeline that allowed them to calculate dates over spans of thousands of years with a mathematical elegance that remains stunning today. Unlike the cyclical calendars of many other cultures, the long count provided a unique, forward-moving count of days from a fixed starting point, a mythological dawn of creation that scholars place in the year 3114 BC according to our calendar. The mechanics of the long count are a testament to Maya mathematical genius. They used a base 20 or vigesimal numbering system, which is far more complex than our base 10 system. This system included the concept of zero, a revolutionary abstract idea that many other contemporary cultures lacked, and it allowed them to perform incredibly sophisticated calculations. A typical long count date is written as a series of 5 components, each representing a different order of magnitude separated by dots. These components count the number of days, known as kayin, then progress through larger units, the winal 20 kayin, the ton 18 winal or 360 days, the kayaton 20 ton, and finally the bakton 20 kayaton or about 394 years. This hierarchical structure enabled priests and scribes to record historical events and future prophecies with pinpoint accuracy across vast stretches of time, an intellectual achievement of staggering proportions. But how did they achieve such breathtaking precision in tracking celestial bodies without telescopes or advanced optics? The answer lies in generations of relentless, naked-eye observation. Maya astronomer priests meticulously charted the movements of the sun, moon, and planets from elevated temple platforms and specially designed observatories like the Caracol at Chichen Itza, with its windows aligned to key astronomical events. They recorded their findings in intricate bark paper codices using a complex system of glyphs. Their calculations for the solar year were more accurate than those used in Europe at the same time, they understood the 584-day cycle of Venus with extraordinary precision, and they could predict solar eclipses. This was not guesswork, it was hard data accumulated and refined over centuries, transformed into reliable predictive models through their advanced mathematics. This leads us to one of the greatest modern scholarly puzzles, the GMT correlation constant. The mystery is not about the Maya calendar's internal accuracy, but about how it aligns with our own Gregorian calendar. How do we convert a Maya long count date into a specific day on our calendar? This problem of correlation has been debated for over a century. The most widely accepted solution, proposed by scholars Joseph Goodman, Juan Martínez Hernández, and J. Eric S. Thompson. Hence, the GMT constant involves cross-referencing Maya dates with historical events recorded by the Spanish, astronomical events like eclipses that are mentioned in Maya texts and whose dates we can calculate backwards, and the surviving Maya calendar still in use by some communities today. Pinpointing this correlation was a monumental detective effort, and while the GMT constant is the leading theory, it is not without its challenges, proving that even today, fully unlocking the secrets of Maya time requires a fusion of archaeology, astronomy, and historical sleuthing. Ultimately, the Maya system reveals a civilization with a radically different conception of time itself. For them, time was not a simple, neutral stream, but a sacred force carried by burdensome gods. Each day had its own spiritual identity and destiny, and the complex cycles of their calendars were meant to reveal the divine patterns woven into the fabric of existence. The completion of a major cycle, like the much-discussed end of the 13th Bacton in the year 2012, was not a prophecy of doom but a moment of profound spiritual renewal, a turning over of a great cosmic page. Their calendars were tools for harmonizing human activity with the rhythms of the gods and the cosmos, making the Maya not just master timekeepers, but brilliant philosophers of time, whose legacy challenges us to consider the deeper meaning behind the relentless tick of the clock. While the Maya were charting vast cosmic cycles on the other side of the world, Chinese engineers were mastering the flow of time itself, not by observing the sky, but by harnessing the element of water. Our next mystery takes us into the heart of ancient China's imperial courts, where the clepsydra, or water clock, evolved from a simple time-measuring vessel into an astonishingly complex mechanical marvel. These weren't just clocks, they were sprawling, multi-story automata, spectacular displays of imperial power and technological prowess that integrated precise timekeeping with astronomical modeling and theatrical entertainment on a scale the world wouldn't see again for centuries. The most sophisticated of these devices, developed during the Song dynasty around the 11th century AD, represent a breathtaking peak of hydraulic engineering that seems to defy its own era. The basic principle of a clepsydra is simple. Water drips at a constant rate from one reservoir into another, and the rising water level in the receiving vessel indicates the passage of time, often with a float and indicator rod. But Chinese engineers, driven by a mandate for perfect accuracy from the imperial astronomers, quickly identified and solved the fundamental flaw in this design. As the water level in the supply tank decreases, the water pressure drops, causing the flow to slow down and making the clock increasingly inaccurate. Their ingenious solution was the overflow tank, or constant level tank, an intermediary reservoir that received water from the main supply. This tank had an overflow siphon that ensured it was always filled to exactly the same level, meaning the pressure of the water flowing out to the time-indicating vessel remained perfectly constant. This was a stroke of genius that transformed the water clock from a rough estimate into a precision instrument. This quest for precision didn't stop there. The most famous of these masterpieces was the astronomical clock tower designed by the brilliant polymath Su Song in the year 1090 AD. This colossal structure, towering over 30 feet high, was a symphony of hydraulics and mechanics. Its heart was a massive water wheel that functioned like the escapement in a modern mechanical clock. As water from the constant level tank filled a series of precise buckets on the wheel's rim, the weight would trip a mechanism, allowing the wheel to rotate one step at a perfectly regulated pace. This intermittent motion, achieved centuries before similar European verge escapements, was the clock's steady pulse, but Su Song's ambition went far beyond merely powering a dial. This regulated power source drove an armillary sphere on the top floor, a complex bronze model of the universe with rings representing the celestial equator, the ecliptic path of the sun, and the orbits of stars and planets. Simultaneously, inside the tower, it powered a celestial globe that mirrored the motions of the armillary sphere, and most spectacularly, a procession of automated mannequins that would emerge from doors at set intervals to ring bells, strike gongs, or hold up tablets announcing the hour. This incredible convergence of functions presents our central mystery. How did they achieve such integrated mechanical complexity so early? The clock tower was a single machine performing three distinct, simultaneous functions: precise timekeeping, astronomical demonstration, and automated spectacle. This required an intricate system of shafts, gears, and drives, all powered by that single, slowly turning water wheel. The gearing ratios needed to translate the wheel's rotation into the different speeds for the celestial models, and the automata would have required incredibly sophisticated mathematical calculation and metallurgical skill to cast the complex bronze gear trains. The knowledge behind this seems to have emerged almost fully formed, suggesting a long, now lost tradition of mechanical engineering that was meticulously documented by Su Song himself in a detailed text. Yet the physical artifacts themselves have almost entirely vanished, leaving us with descriptions so advanced they were once doubted by historians. The purpose of these monumental devices was as multi-layered as their mechanisms. On a practical level, they were the ultimate authority on time for the empire, crucial for the astrologer officials who determined the exact dates for imperial ceremonies, agricultural cycles, and state rituals. The astronomical displays provided a working model of the cosmos for scholarly study, but on a deeper level they were potent political theater, a machine that could predict celestial events and announce the time with divine pageantry was a powerful symbol of the emperor's mandate of heaven, his divine right to rule bestowed by the cosmos itself. By demonstrating a perfect mechanical control over the very flow of time and the motions of the heavens, the imperial court was showcasing its harmony with the universal order. The eventual decline and loss of this technology is itself a historical puzzle, perhaps a victim of shifting dynasties and philosophical movements that turned away from mechanical wonder. Yet for a time, these hydraulic marvels stood as perhaps the most advanced timekeeping devices on Earth, a testament to a civilization that saw time not just as something to be measured, but as a force to be orchestrated. Leaving behind the monumental water clocks of China, our journey takes a surprising turn into the realm of the truly speculative, with an artifact so enigmatic that it seems to challenge the very timeline of human innovation. In the basement of the National Museum of Iraq in Baghdad sits a small, unassuming clay jar roughly the size of a man's fist. Dating back to the Parthian period, sometime between 250 BC and 250 AD, this ordinary-looking pot was unearthed in 1936 near the village of Kujat Rabu. It would have remained just another ancient storage vessel if not for its perplexing contents: a copper cylinder carefully soldered with a 60-40 lead tin alloy surrounding an iron rod, all sealed at the top with an asphalt plug. This peculiar combination of materials immediately struck its discoverer, German archaeologist Wilhelm Koenig, as something far more extraordinary. He proposed a theory that was both electrifying and heretical. Could this be the remains of an ancient galvanic cell, a primitive battery? The principle behind the so-called Baghdad battery is simple yet profound. If the jar were filled with an acidic or alkaline electrolyte liquid, such as vinegar or grape juice, a chemical reaction would occur. The acidic liquid would interact with the two different metals, the copper cylinder and the iron rod, creating a potential difference or voltage between them. In essence, this setup would form a basic electrochemical cell, capable of generating a small but measurable electric current, estimated to be around 1 volt. To test this theory, modern researchers have constructed numerous replicas, and indeed, when filled with the right electrolyte, these reproductions do produce a low-level electrical charge. This practical evidence forms the core of the controversial claim, suggesting that ancient Mesopotamian craftspeople might have stumbled upon the principles of electricity over 1,000 years before Alessandro Volta's famous battery in the early 1800s. This fascinating possibility naturally leads to a deeper, more speculative mystery. If it was a battery, what was its purpose? Mainstream archaeology remains deeply skeptical, offering more mundane explanations. The most widely accepted theory posits that the jars were used for sacred or practical storage, perhaps to hold precious scrolls made of organic materials like papyrus or parchment. The asphalt seal would have provided an airtight environment, protecting the contents from moisture and decay. The metal rods and cylinders in this view were simply decorative or structural components of a sealed container. Other scholars suggest they could have been used in electroplating to deposit a thin layer of one metal onto another, such as gold onto silver for jewelry. There is, however, no definitive archaeological evidence from the period, such as electroplated artifacts, to directly support this application. But let's entertain the more thrilling possibility for a moment. If these devices were indeed primitive batteries, their potential use in timekeeping, while highly speculative, opens a door to a lost chapter of technology. A steady, low-level electrical current could theoretically have been used to power a simple timing mechanism. Imagine a device where the electric current slowly dissolved a thin wire or etched a marked surface at a predictable rate. The completion of this process, when the wire broke or a mark was reached, could trigger an alarm or indicate the passage of a specific interval. Alternatively, the current could have been used to electrolyze water, with the accumulation of gas bubbles in a tube serving as a visual timer. While there is no direct evidence for such clocks in the Parthian world, the theoretical framework exists, suggesting that the basic ingredients for an electrochemical timekeeping device were potentially within their grasp. This brings us to the heart of the controversy and the reason this artifact remains such a captivating mystery. The complete absence of any associated devices, wires, or diagrams that would confirm an electrical application is a massive hurdle for the battery theory. We have the potential power source, but we lack the machine it was meant to power. This absence forces us to ask a critical question. Is this a case of modern minds projecting our technological framework onto an ancient object, seeing a battery because we know what batteries are? Or did this culture possess a spark of knowledge, a practical understanding of a natural phenomenon that was never fully developed or was later lost to history? The truth is, we may never know for certain. The artifact stands as a powerful reminder of the gaps in our historical record and the tantalizing possibility that ancient civilizations may have discovered and utilized concepts we believe are uniquely modern. It challenges our linear view of scientific progress and invites us to wonder what other secrets still lie buried, waiting for a curious mind to connect the right pieces and perhaps rewrite history. From the humid jungles of Mesoamerica and the imperial courts of China, we now return to the familiar shores of the Mediterranean, to a mystery not of a single spectacular device, but of thousands of seemingly ordinary ones. Scattered across the vast expanse of the former Greek and Roman worlds, from the sun-baked ruins of North African outposts to the rainy northern frontiers of Britain, archaeologists have unearthed a plethora of portable sundials. Individually, they are fascinating artifacts. Collectively, they present a puzzle that hints at a level of organizational sophistication and knowledge sharing we are only beginning to appreciate. These were not crude, locally made approximations of time, but remarkably precise and standardized instruments that followed complex mathematical principles, suggesting the existence of an ancient network of technical knowledge that allowed a traveler to tell the same time in Gaul as they would in Greece. The design of these portable sundials, often small enough to fit in the palm of one's hand, was deceptively complex. The most common type was the hemispherical dial, or hemicyclium, a concave bronze dish etched with a precise web of hour line. A tiny gnomon, the part that casts the shadow, was suspended over the center of this bowl, but the true genius lay in its adaptability. Many of these dials were not fixed to a single location, they were adjustable. Some came with interchangeable gnomons of different angles, while others featured a sliding mechanism or a series of holes around the rim, allowing the user to calibrate the instrument for different latitudes. This was no simple task. To accurately tell the hour, the user needed to know their approximate latitude and had to align the gnomon correctly to point toward the celestial pole. This implies that the owners of these objects possessed a working understanding of basic spherical astronomy and geometry, concepts we often assume were reserved for elite scholars rather than well-traveled citizens or soldiers. This widespread consistency in design and mathematical principle is what fuels the central mystery. How did this technology become so standardized across such a vast and culturally diverse empire? We are likely looking at the work of a specialized trade of skilled metalworkers who followed pattern books or shared templates. These artisans would have required training in the underlying Greek geometry that made the dials work, particularly the theories developed by astronomers like Hipparchus, who, in the 2nd century BC, laid the groundwork for projecting the celestial sphere onto a flat plane. This knowledge appears to have been effectively industrialized and disseminated, creating a kind of ancient mass production for the educated elite. The presence of these dials in military camps suggests that knowing the precise time was important for coordinating duties, watch changes, and perhaps even military campaigns, indicating that timekeeping was integrated into the logistical framework of the Roman state. This leads to a tantalizing and broader question: was there a conscious effort toward time standardization in the ancient world? While the Romans never achieved a universal time zone system like we have today, the proliferation of these accurate, portable timepieces suggests a powerful desire to synchronize human activity across great distances. The very fact that a sundial purchased in Alexandria would function correctly in Rome after a simple adjustment points to a shared understanding of time as a measurable, universal constant. It hints at a world that was more interconnected and scientifically pragmatic than we sometimes imagine, where a merchant, a soldier, or a provincial official could carry a precise piece of the cosmos in their pocket and use it to order their day according to the same principles that govern the capital. This network of portable time may have been one of the intangible threads that helped bind the vast and sprawling Roman Empire together, creating a silent, solar-powered rhythm for commerce, administration, and daily life. Stretching for miles across the Brittany countryside in northwestern France lies one of the most awe-inspiring and perplexing megalithic sites in all of Europe, the alignments of Karnak. Here, amidst the quiet fields, stand over 3,000 prehistoric standing stones arranged in long, parallel rows that seem to march with purposeful intent across the landscape. While many are familiar with the solitary grandeur of Stonehenge, Karnak offers a different kind of mystery, one of scale, repetition, and a potential celestial purpose that is only now coming into focus. For centuries, these stones were attributed to mythical Roman legions turned to stone or considered the work of giants. But modern archaeology and archaeoastronomy are revealing a far more fascinating truth: that this vast open-air monument may represent one of humanity's most ambitious and patient attempts to map the complex dance of the moon. The sheer scale of construction at Karnak is almost incomprehensible. The site is not a single circle but a sprawling complex of multiple alignments, the most famous being Lamanic, Kermario, and Kerleskan. At Lamanic alone, 1,099 stones are arranged in 11 converging rows stretching over 3,000 feet. These are not randomly placed boulders. There is a clear organizational logic. The stones generally decrease in height from west to east, and the rows themselves appear to be carefully oriented. For a long time, the prevailing theory was that these were processional avenues leading to sacred burial mounds which dot the area. But a more compelling, albeit complex, theory has gained traction, that the alignment served as a gigantic, permanent observatory for tracking the moon's subtle long-term movements, a project that would have required generations of dedicated observation. This theory centers on the moon's major standstill, a celestial event that occurs only once every 18.6 years. Unlike the sun, which rises and sets within a fixed range on the horizon throughout the year, the moon's rising and setting points migrate along the horizon in a much wider arc over this long cycle. At the peak of this cycle, the moon reaches its most extreme northerly and southerly positions, a phenomenon known as a major standstill. This is a subtle effect, barely noticeable year to year, but over a decade and a half the pattern becomes clear. Researchers like Alexander Thom and later Clive Ruggles have proposed that the Karnak alignments are precisely calibrated to these lunar extremes. The fan-shaped arrangement of the rows, they argue, acts like a giant gun sight, framing the horizon and providing fixed lines against which to observe the moon's slow creep to its most extreme points. A priest or astronomer standing at one end of an alignment could use the converging rows to pinpoint the moon's position on the horizon with remarkable accuracy, turning the entire landscape into a precise measuring instrument. This immediately raises the profound and haunting question that hangs over so many Neolithic sites. How could a prehistoric society with no written language achieve such a long-term, precise understanding of astronomy? Tracking an 18.6-year cycle is an endeavor that spans generations. It requires not only meticulous observation but a sophisticated method of recording and passing that knowledge down orally through many lifetimes. The builders would have had to notice a tiny shift in the moon's position each year, remember it, and then patiently wait nearly 2 decades for the pattern to complete and begin again. This suggests a highly stable, culturally continuous society with a dedicated class of astronomer priests whose sole purpose was to watch the sky and preserve this hard-won knowledge through stories, songs, and rituals. The monument itself may have been the ultimate record, a stone library of celestial data that could not be lost. The purpose of this incredible effort likely went far beyond mere curiosity. In a society utterly dependent on the cycles of nature, the moon was a powerful force governing the tides and illuminating the night. Its association with cyclical renewal, dying, and being reborn each month would have made it a potent symbol in their spiritual life. The ability to predict its most extreme movements could have been seen as a form of cosmic power, a way to demonstrate a connection to the divine order. By building these massive stone rows, the community was not just observing the moon, they were anchoring its celestial power to their own territory, weaving their identity into the fabric of the cosmos. The alignments were probably the centerpiece of major rituals conducted during significant lunar events, gatherings that reinforced social bonds and the authority of the leaders who held the keys to this celestial knowledge. Karnak, therefore, stands as a silent testament to human patience and our eternal desire to find meaning in the night sky, a monument built not in years but over centuries with the moon as its timeless guide. Far from the megalithic rows of Karnak on the vast and ancient continent of Australia, we find a timekeeping tradition of a profoundly different nature, one that is not measured in monumental stones aligned to distant planets, but in the intimate, daily rhythms of the land itself. For over 65,000 years, Aboriginal Australians have cultivated a deep, symbiotic relationship with their environment, developing a form of timekeeping that is less about tracking celestial mechanics and more about listening to the Earth's own heartbeat. This knowledge was often encoded in seemingly simple stone arrangements, but to dismiss them as primitive is to completely miss their sophistication. These structures are not crude calendars, they are the physical manifestation of a complex and holistic ecological science, representing perhaps the most sustainable and deeply connected timekeeping system ever conceived. Scattered across the Australian landscape from Victoria to the arid interior are a variety of stone arrangements whose purposes were long misunderstood by European settlers. Unlike the towering monoliths of Europe, many of these are low to the ground, consisting of circles, lines, or cairns of rocks that might appear random to an untrained eye. The Wurdi Yuang stone arrangement in Victoria, for instance, is an egg-shaped ring of about 100 basalt stones, with its major axis carefully aligned to the setting sun at the summer and winter solstices. But the true genius of these sites often lies beyond solar alignment. They function as multi-layered calendars where a single stone might mark the day a particular tuber becomes edible, another the time when a specific moth species emerges, and a third the arrival of a migratory bird. This creates a living calendar where time is not an abstract number on a dial, but a series of predictable, interconnected events within the local ecosystem. This approach reveals an astronomical system of breathtaking nuance. Aboriginal knowledge systems often divide the year not into 4 arbitrary seasons, but into multiple, detailed segments based on subtle environmental cues. For example, many groups recognize 6 to 8 distinct seasons, each defined by a precise combination of celestial, weather, and biological events. The Gari word calendar in southeastern Australia includes season of the orchid, when specific terrestrial orchids bloom, and season of the acacia, when the silver wattle flowers. The appearance of the Pleiades star cluster in the dawn sky is a well-known signal for many groups, but its meaning changes with location. For some, it signals the start of the cool weather and the movement of fish upriver, while for others, it's a warning that frosts are coming that will damage certain plants. This is astronomy deeply contextualized by ecology. The profound mystery and wonder of this system lie in the question of its endurance. How was this immense body of knowledge, spanning thousands of years and encompassing the entire continent, preserved and accurately transmitted across hundreds of generations without a written language? The answer is a cultural masterpiece of oral tradition. This knowledge was not kept in a book but was woven into the very fabric of society through songlines or dreaming tracks. These are epic navigational routes that crisscross the country, where every landmark, waterhole, and turning point is encoded in a song. The songs are, in effect, sung maps, but they are also intricate oral encyclopedias. A song for a particular area might contain verses that detail the time of year when the honey ants are fattest, the medicinal plants that are in season, and the stars that are visible overhead, all in perfect sequence. The act of walking the songline and singing the song was how knowledge was rehearsed, verified, and passed on, ensuring its survival for millennia. Ultimately, these stone arrangements and the vast knowledge system they represent were about far more than marking time. They were about sustaining life and maintaining balance. This was a practical science for survival, dictating the most sustainable times to hunt, gather, and burn the land for regeneration. But it was also a spiritual philosophy that saw humans not as separate from nature, but as active participants in its cycles. A stone marking the spawning season of a fish was a reminder of both a food source and a reciprocal responsibility to ensure that source remained abundant for generations to come. This represents a form of timekeeping that is inherently ethical and sustainable, where understanding the schedule of the natural world came with a duty to protect it. In an age of climate crisis, this ancient stone-based wisdom challenges our modern disconnect from the environment, offering a timeless lesson that the most accurate clock is not one that measures abstract seconds, but one that listens to the world breathing. High in the Andes, perched among the mist-shrouded peaks of Machu Picchu, sits a granite carving that seems to both challenge the sky and be one with the mountain itself, the Ingenuity stone. Its name, often translated as the hitching post of the sun, evokes a powerful and poetic image, a civilization so in tune with the cosmos that they built a stone tether to hold their celestial deity in place. This was no ordinary altar. It was a supremely sophisticated astronomical instrument, a masterpiece of Incan engineering and spiritual belief carved directly from the living bedrock of the mountain. Unlike the portable dials of Rome or the geared mechanisms of Greece, the Ingenuity is immovable, eternal, and profoundly connected to its specific, sacred location, representing a unique approach to measuring time that was deeply interwoven with the Incas' divine geography. The precision of the Ingenuity's design is what immediately captivates modern observers. The stone itself is a complex, multi-tiered sculpture, rising from a base that mirrors the contours of the surrounding sacred mountains, the Apus. At its pinnacle is a slender, vertical gnomon, a precisely carved pillar that casts a definitive shadow onto the stone platform below. This platform is not a blank slate. It is carefully shaped with angles and planes that correspond to key solar events throughout the year. The most dramatic demonstration occurs during the equinoxes on March 21st and September 21st. On these 2 days, when the sun sits directly above the equator and day and night are of equal length, the shadow cast by the gnomon becomes perfectly vertical. It doesn't just point to a line. For a few sacred moments, the shadow effectively disappears, as if the sun has indeed been hitched directly to the stone, its power captured and held firm by the Inca priests. This is not a rough approximation. It is an observation of stunning accuracy, achieved through stonework of breathtaking skill. This level of accuracy forces a difficult question. How did the Inca, working without iron tools, the wheel, or a formal written language, achieve such flawless astronomical alignment in their stonework? The answer lies in a combination of generational knowledge and an almost supernatural mastery of stone. Incan stonemasons were arguably the best in history. They worked granite and other hard stones using only harder stones, bronze tools, and abrasive sand, patiently pecking, grinding, and polishing surfaces to a faultless finish. They understood geometry and angles through practical application, not abstract theory. The creation of the Ingenuity would have required years, perhaps decades, of patient observation. Master stonemasons would have worked in concert with astronomer priests, the amoters, who marked the sun's critical positions at solstices and equinoxes over many annual cycles. The stone was then gradually carved and refined, its angles adjusted minutely with each passing year until the shadows fell exactly where the priests demanded. This was a project that blended immense patience with impeccable craftsmanship, all dedicated to capturing the rhythm of the sun. But was this exquisite device a practical calendar for agriculture or a profoundly sacred altar for the gods? The evidence strongly suggests it was both, with the spiritual purpose taking clear precedence. On a practical level, the Ingenuity's ability to mark the equinoxes and solstices would have been invaluable for managing the agricultural cycle in the challenging high-altitude environment. Knowing the exact time to plant and harvest was a matter of survival. However, for the Inca, the sun, or in Thai, was not merely a celestial timekeeper. It was the divine progenitor of their empire, the literal father of their first emperor. To control its movement was an act of supreme religious importance. The ceremonies performed at the Ingenuity were not just celebrations of a solar event. They were essential rituals to ensure the sun's continued journey across the sky. The Inca believed that if they failed to properly hitch the sun during its lowest point at the winter solstice, it might continue its journey away from the earth, plunging the world into permanent darkness and chaos. The priest's act of observation was an act of cosmic maintenance, a ritual that sustained the universe itself. The true, haunting mystery of the Ingenuity may lie in what was lost. The Spanish conquistadors, in their campaign to extinguish Inca religion, systematically sought out and destroyed these solar observatories. Machu Picchu, hidden high in the mountains, escaped this fate, leaving its Intihuatana as one of the very few to survive intact. This makes it an incredibly rare and precious window into the Incan mind. It represents a worldview where astronomy, architecture, religion, and political power were inseparable. The stone is not just aligned with the sun, it is aligned with the sacred mountains and the flow of rivers, integrating the cycles of the sky with the spirit of the earth. It stands as a silent stone sentinel, a testament to a civilization that sought not just to observe time, but to participate in it directly, to engage in a sacred dialogue with the cosmos to ensure the balance and continuity of all life. While the Incas were building monolithic solar tethers high in the Andes, a civilization on the arid plains of ancient Persia was mastering time in a completely different way by harnessing the hidden, steady flow of water deep beneath the desert. Our next mystery takes us into the cool, dark world of the Qanat, a marvel of hydraulic engineering that did far more than just bring life-giving water to the surface. These sophisticated underground channels were, in fact, elaborate timekeeping networks, their very design calibrated to measure the passage of hours and days with a reliability that governed entire communities. In a land where water was more precious than gold, the Qanat system became the beating heart of civilization, and its rhythmic pulse was the most accurate clock imaginable. The construction of a Qanat was a monumental undertaking, a testament to human perseverance and collective effort. It began with the discovery of an aquifer at the base of a mountain. From this water source, teams of skilled workers known as mucanis would tunnel horizontally, sometimes for dozens of miles, at a meticulously calculated, gentle slope just steep enough to allow the water to flow by gravity, but not so steep as to cause erosion. Vertical access shafts were dug at regular intervals, not only for removing excavated material and providing ventilation, but also for the crucial ongoing maintenance that kept the channel clear. This created the iconic appearance of Qanats on the surface, a long line of craters, like a string of pearls stretching from the foothills to the Palo lands below. The true genius of this system was its sustainability. By keeping the water underground, it was protected from the evaporating heat of the desert sun, ensuring a steady, year-round supply for drinking, bathing, and most importantly, irrigation. This is where the system transforms from a mere water conduit into a sophisticated timekeeping device. The distribution of water to different farms and villages was a matter of supreme importance, and it was managed with impeccable fairness through a unit of time measurement based on the Qanat itself. The primary unit was the jarib or panier, which represented the amount of time it took for a specific volume of water to flow from a central outlet and irrigate a standard parcel of land. But how do you measure that time without a mechanical clock? The answer lay in the ingenious use of a simple bowl. A trained watermaster, known as a merab, would use a bronze or copper bowl with a small hole in the bottom. He would place this bowl in a small pool of water at the distribution outlet, and the time it took for the bowl to sink, filled to a certain level by the incoming water, defined the fundamental unit. This could be a matter of minutes, and the sinking of the bowl marked one share of water time for a farmer. This method, while simple in concept, required a deep, localized understanding of physics that we might easily overlook today. The merab was a master of his craft. He knew that the sinking time of the bowl could be affected by factors like the mineral content of the water, which changed its density, or the temperature, which affected the viscosity. He would calibrate his bowl and his measurements for the specific conditions of his Qanat. Furthermore, the flow rate of the Qanat itself was not constant throughout the year. It would be higher after the spring melt and lower in the late summer. The merab possessed generational knowledge of these annual fluctuations and would adjust the water allocation schedules accordingly, ensuring that the measurement of time remained fair and equitable even as the natural world changed around it. This was a dynamic, living system of timekeeping perfectly adapted to its environment. The role of the Merab elevates this system from a technical process to a social and legal institution. This individual was more than a maintenance man. He was a respected judge, a timekeeper, and a community leader. His authority was absolute when it came to water rights. Farmers would receive their allotted time based on the size of their landholding, and the Merab would oversee the opening and closing of the gates at the distribution points, his sinking bowl serving as the unchallengeable arbiter of whose turn it was. This system prevented conflicts and ensured the survival of the entire community. The schedules were often complex, with irrigation cycles that could last for days, and the Merab would keep detailed records, sometimes on clay tablets, of who had received water and for how long. His knowledge was a sacred trust passed down from father to son, preserving not just the technical details but the principles of justice and cooperation that the entire society depended on. In the end, the Persian Qanat represents a philosophy of time that is deeply grounded in community and necessity. Unlike a sundial that tracks the cosmic journey of the sun or a water clock that measures abstract hours, the Qanat clock measured something immediately vital: the right to life itself. Its unit of time was not an hour or a minute, but a share of a community's most precious resource. This system created a rhythm of life that was perfectly synchronized with the natural hydraulic cycle and the needs of agriculture. It stands as a profound example of how human ingenuity can create order and fairness in a challenging environment, turning the simple, relentless flow of water into the very meter of civilization. The Qanats, many of which are still in use today, are not just relics of ancient engineering. They are a lasting testament to a society that understood time not as something to be observed, but as something to be shared. Venturing from the ancient water laws of Persia, we now set sail into the foggy, treacherous waters of the North Atlantic, where Norse explorers faced a navigational nightmare. How did the Vikings, those intrepid sea raiders and traders, manage to cross vast, open ocean between Norway, Iceland, and even Greenland without the aid of a magnetic compass, often under the perpetually overcast skies of the northern latitudes? The answer may lie in a legendary device mentioned in their sagas, a crystal that could seemingly conjure the sun from behind the clouds. This is the enduring mystery of the Viking sunstone, a tool that straddles the line between myth and sophisticated optical science, offering a glimpse into a potentially lost art of celestial timekeeping and navigation. The primary historical source for the sunstone comes from the 13th century Icelandic saga detailing the life of King Olaf. In one passage, the king is challenged to identify the sun's position on a cloudy winter day. He holds up a mysterious solarstein or sunstone, looks at the sky, and correctly points to the sun, much to the amazement of his followers. Another saga references a similar crystal being used to check the sun's position when the weather was foggy or snowy. For centuries, these accounts were dismissed as mere folklore, poetic metaphors for a leader's divine insight. That changed in the 1960s when Danish archaeologist Thorkild Ramsku proposed a startlingly practical theory. He suggested the sunstone wasn't a myth at all, but a real navigational tool made from a specific type of crystal that could detect the polarization of sunlight, a phenomenon invisible to the naked human eye. The science behind this theory is as elegant as it is clever. Even on a completely overcast day, sunlight penetrating the cloud cover becomes polarized, meaning its light waves vibrate in a specific direction oriented around the hidden sun. Certain transparent crystals, like Iceland spar, a form of calcite common in Scandinavia, possess a property called birefringence. When you look through this crystal, you see a double image. By rotating the stone and observing how the intensity of this double image changes, a skilled user can find the angle where the two images appear equally bright. This alignment points directly to the sun's position in the sky, even if it is completely obscured from view. It effectively turns the entire sky into a giant compass, with the crystal acting as a filter to decipher its hidden patterns. A navigator could hold the stone up to the sky, rotate it until the light patterns matched, and know exactly where the sun was, allowing them to determine cardinal directions and approximate the time of day. This leads to the tantalizing question of how these crystals were integrated with other Norse navigational methods. A sunstone alone gives a direction, but for true open ocean wayfinding, the Vikings needed to know their latitude. They almost certainly used a form of primitive latitude sailing, relying on known reference points. They might have used a simple shadow board, a wooden disc with a central gnomon, to measure the sun's altitude at its highest point each day. By knowing the sun's height at a specific time of year from their home port, they could sail east or west until they reached a coastline where the sun's altitude matched their destination, then turn and sail directly north or south along that latitude line. The sunstone would have been the crucial tool that enabled them to take these sun altitude measurements on cloudy days, maintaining their course when other celestial cues vanished. It was the key that unlocked reliable travel under the worst conditions. Yet, for all the compelling theory, a profound archaeological mystery remains. Why have no sunstones ever been found on a Viking shipwreck? We have found their ships preserved in stunning detail, their tools, their weapons, and their personal belongings, but not a single definitive sunstone has been recovered from a nautical context. The absence of physical evidence is the biggest hurdle for the theory. Some small crystals of Iceland spar have been found in the wreck of an Elizabethan warship that sunk in 1592, a much later period, but the link to the Vikings is circumstantial at best. This lack of proof forces us to consider other possibilities. Perhaps the sunstone was so valuable it was never left on board, or maybe it was a rare tool used only by a few expert navigators. It's also possible the crystals, being relatively fragile, simply did not survive centuries on the seabed. The truth is, we may never have a smoking gun, and the sunstone may forever remain in the realm of highly plausible but unproven ancient technology. Ultimately, whether future archaeological discoveries confirm its existence or not, the concept of the Viking sunstone reveals a tremendous amount about Norse ingenuity. It represents a profound understanding of the natural world, an ability to harness subtle physical properties of light and crystal for survival. This wasn't magic, it was applied science, a brilliant workaround for one of the most challenging navigational environments on Earth. It symbolizes the Vikings not as mere brutish raiders, but as master mariners who could read the secrets of the sky itself, using a piece of their own land to conquer the open ocean and connect a vast network of trade and exploration that stretched from North America to the edges of Asia. The sunstone stands as a powerful testament to human curiosity and adaptability, proving that sometimes the most advanced technology isn't complex machinery, but a simple crystal held to the sky by a knowing eye. Leaving behind the Norse mariners and their sun-seeking crystals, we journey now to the ancient universities and bustling temple complexes of India, where time was not just measured but was poured, drop by deliberate drop, in a symphony of hydraulic precision. Here, timekeeping was elevated to both a science and an art form, embodied in magnificent devices known as Ghataka yantras. These were not the simple water clocks of other cultures. They were monumental, intricately engineered water clocks designed to measure time with a level of accuracy that supported everything from complex astronomical calculations to the exact timing of sacred rituals, proving that the flow of water could indeed become the pulse of an entire civilization. The design and operation of a Ghataka yantra were exercises in brilliant practical physics. At its heart was the principle of the clepsydra, but executed on a grand and meticulously calibrated scale. The most common design featured a large, floating bowl made of copper or bronze with a precisely drilled hole in its bottom. This bowl was placed in a larger vessel filled with water. As water slowly seeped through the hole, the bowl would lose buoyancy and eventually sink after a fixed period. This period was known as a gati, a unit of time equivalent to about 24 of our modern minutes. The genius, however, lay in the systems built to ensure this measurement remained constant. To counter the natural decrease in water pressure that would slow the flow as the main reservoir emptied, many designs incorporated a constant level tank, much like the Chinese clepsydra, ensuring the head of water pressing on the hole never changed. The size of the hole and the thickness of the bowl's metal were calculated with astonishing exactness to achieve the desired sinking time, a testament to a deep empirical understanding of hydrodynamics. This remarkable accuracy was not for mere convenience. It was the essential bedrock for two pillars of ancient Indian society: astronomy and religion. In the great centers of learning like the universities of Nalanda and Takshashila, astronomer scholars relied on the Gatika Yantra to time their celestial observations. To chart the movement of planets and stars with any hope of precision, they needed to know exactly how much time had elapsed between sightings. The consistent, rhythmic sinking of the bowl provided this fundamental data, allowing them to develop and refine complex mathematical models of the cosmos. Their calculations of planetary orbits, the length of the solar year, and the prediction of eclipses were all dependent on the reliable beat of this water clock. It was, in effect, the precise timer that made advanced Indian astronomy possible, a tool that translated the steady drip of water into a map of the heavens. Simultaneously, within the sacred walls of temples, the Gatika Yantra governed the divine schedule of the gods. Hindu rituals or pujas are highly time-sensitive. Specific ceremonies must be performed at exact moments of the day, such as at sunrise, noon, and sunset, or during astrologically auspicious windows known as muhurtas. The responsibility for announcing these critical times fell to temple attendants who monitored the water clock. The sinking of the bowl would trigger the striking of a gong or the blowing of a conch shell, signaling the priests to begin their invocations. This transformed the Gatika Yantra from a scientific instrument into a sacred voice, a mechanical priest that ensured the cosmic order was maintained through perfectly timed devotion. The synchronization of human ritual with cosmic rhythm was believed to sustain the universe itself, and the water clock was the indispensable link that made this harmony possible. Perhaps the most captivating aspect of these devices was their role in public timekeeping, making them a central feature of daily civic life. Large, ornate Gatika Yantras were often installed in public squares or temple courtyards, functioning as civic clocks for the entire community. Their operation was a public spectacle, often involving elaborate automata. As the bowl sank, it might trigger a mechanism causing a small statue to strike a drum, or a ball to roll down a chute and land in a metal basin with a loud clang. This auditory signal allowed everyone in the vicinity, merchants in the market, students heading to class, farmers in the fields, to coordinate their activities. In an era before personal timepieces, the communal sound of the water clock created a shared temporal rhythm, structuring the day for entire cities and fostering a collective sense of order and punctuality that was deeply integrated into the social and economic fabric of ancient India. The legacy of the Gatika Yantra is a powerful reminder of a culture that approached time with a unique blend of mathematical rigor and spiritual reverence. It wasn't seen as a mere resource to be managed, but as a sacred, rhythmic force that connected human activity to the cosmos. The steady, sinking bowl embodied a philosophy where science and faith were not in opposition, but were two complementary paths to understanding the universe. These ingenious devices provided the precise intervals needed to unravel the mysteries of the stars, while also ensuring that the prayers meant to honor those very stars occurred at the perfect moment. They stand as a testament to the fact that some of history's most profound advancements were born from the desire to listen to the quiet, rhythmic music of the world, whether it was written in the stars or measured in a drop of water. Now we venture from the rhythmic water clocks of India into the shadowy, torch-lit halls of an Egyptian temple, where a single bizarre carving has sparked a controversy that bridges ancient mysticism and modern technology. Deep within the crypts of the Temple of Hathor at Dendera, the same site that gifted us the magnificent zodiac, there is another relief that has become the subject of fierce debate. It depicts a strange scene. A large, wavy serpent is contained inside an elongated, tear-shaped object that looks startlingly like a giant, transparent light bulb. This serpent is held aloft on a pillar by a jed, the symbol of stability, while a person stands beneath it as if in attendance. To some, this is clear evidence of advanced, lost technology, an ancient Egyptian light bulb. But to archaeologists and historians, this interpretation misses a far more fascinating and probable truth, one that connects this image directly to the sacred measurement of time and the very essence of Egyptian spiritual belief. The so-called Dendera light theory is certainly captivating. Proponents point to the bulb-like shape, the serpent resembling a glowing filament, and the pillar as an insulator, suggesting the scene represents the operation of an electrical device. They argue the surrounding figures are priests performing some kind of ritual with this wondrous technology. While this makes for a fantastic story, it fundamentally misunderstands the context and the rich symbolic language of Egyptian art. There is no archaeological evidence for electrical generators, wires, or glass bulbs anywhere in ancient Egypt. The relief is surrounded by other, more easily interpreted scenes that are clearly mythological, featuring well-known gods and traditional symbols. To isolate this one image and give it a modern, technological reading is to ignore the entire library of cultural meaning that surrounds it. So if it is not a light bulb, what could this enigmatic scene actually represent? The most widely accepted explanation by Egyptologists is that it is a symbolic depiction of a profound moment of creation, deeply tied to the Egyptian understanding of time's cyclical nature. The central element is not a light bulb but a lotus flower, a potent symbol of birth and rebirth. In Egyptian mythology, the sun god Ra was believed to have emerged from a lotus blossom that rose from the primordial waters at the dawn of time. Each day, this act of creation was repeated with the sunrise. The filament is not a wire but a snake, a creature synonymous with transformation and regeneration due to its ability to shed its skin. This is not just any snake, it is most likely the snake goddess Wadjet or the deity Nehebkau, emerging from the lotus to begin a new cycle. The jed pillar represents stability and endurance, the force that allows this cycle to continue eternally. The entire scene is a mythological map illustrating the moment the sun is born anew from the cosmic flower. This interpretation leads us directly to its potential function as a sacred timekeeping device. For the Egyptians, time was not a linear progression but an endless cycle of repetition, mirroring the daily journey of the sun. The key to this cycle was the heliacal rising of Sirius, the star whose reappearance in the dawn sky after a period of invisibility heralded the annual flooding of the Nile. This event was the cornerstone of the Egyptian calendar, marking the start of the new year and ensuring the fertility of the land. The Dendera relief could be a symbolic representation of this critical celestial event. The emerging serpent from the lotus could symbolize Sirius itself, bursting into view to announce the renewal of time and the life-giving inundation. The priest beneath it isn't an electrician. He is a timekeeper, a guardian of the calendar, perhaps performing a ritual to ensure the star and the flood arrive on schedule, maintaining the cosmic order or mat. Therefore, the true power of the Dendera relief may lie in its role as a ceremonial instrument for measuring sacred time intervals. It wasn't a mechanical clock but a theological one. The relief itself, located in a dark crypt, could have served as a focal point for rituals performed during these pivotal moments of the year. During a ceremony at the summer solstice or at the rising of Sirius, the flickering light of torches might have been played across the carved stone, making the serpent seem to writhe and come alive within its flower, dramatically re-enacting the moment of creation for the attending priests. This performance would have been a way to hitch the celestial event to the earthly ritual, to participate in the cycle and ensure its continuance. It measured time not in hours or minutes, but in epochs and renewals, marking the grand, sacred intervals that defined the Egyptian universe. The mystery of Dendera is not about lost technology, but about a lost way of seeing a world. Where a carving in a dark room was not a diagram for a machine, but a portal to participate in the eternal, repeating rhythm of time itself. Across the vast and diverse cultures of North America, another form of timekeeping emerged, one that was carried in the hand and etched not in stone but in wood. While great empires built towering monuments to track the heavens, many Native American tribes developed a far more portable and personal system, the calendar stick. These were not simple notched logs, they were intricate curated histories and almanacs, each carving a complex story of days, seasons, and celestial events into a slender piece of wood. The mystery they present is not one of lost technology, but of a sophisticated symbolic language that wove together the practical, the sacred, and the historical into a single, enduring record, challenging our understanding of how precise knowledge can be preserved without a written alphabet. The physical creation of a calendar stick was a deeply thoughtful process, often entrusted to a designated keeper within the tribe, a person of great memory and responsibility. The stick itself was typically made from a durable wood like cedar or ash, carefully selected and prepared. The keeper would then use a knife, a sharp stone, or a burning brand to inscribe a series of markings along its length. But these were not mere tally marks. The notation system was remarkably complex and nuanced. A deep, wide gouge might represent a significant event like a major battle or a devastating earthquake. A series of smaller notches could count the passing days or moons. Distinctive symbols were used to mark the changing seasons. A fish for the salmon run, a leaf for the autumn harvest, a particular animal to denote its migration time. Crucially, astronomical events were also recorded. A circle with rays for a solar eclipse, a cluster of dots for the Pleiades star cluster rising at dawn, or a specific pattern to note the winter solstice. Each stick was a unique and layered chronicle, its language known intimately to its keeper and his apprentice. This incredible specificity immediately raises a profound question. How could such precise astronomical and calendrical information be maintained and accurately transmitted across countless generations using only oral tradition and a carved piece of wood? The answer lies in a powerful symbiotic relationship between the object and the individual. The calendar stick was not a standalone data storage device. It was a memory aid, a physical anchor point for a vast and detailed oral history. The keeper, who was often trained from childhood, would hold the stick and use its symbols as cues to recount the full story. Each notch and glyph triggered a detailed narrative, the story of the harsh winter, the celebration of a bountiful hunt, or the omen seen in a comet's passing. The stick ensured the chronological framework remained exact, while the oral tradition preserved the rich context, the lessons, and the cultural meaning behind each event. This combination created a robust and resilient system. Even if a stick was lost, the knowledge could potentially be recreated from the shared memory of the community, guided by the trained keeper. The purpose of these sticks extended far beyond simply marking a new moon. They were the central nervous system of community planning and cultural continuity. On a practical level, they were essential agricultural and ecological guides. By referring to the stick, the keeper could advise when to plant certain crops based on the phase of the moon recorded the previous year, or when to expect the salmon to return to the rivers based on a cycle marked decades earlier. This was a form of hyper-localized, long-term ecological tracking that ensured the tribe's survival, but their function was also deeply spiritual and legal. The sticks served as an irrefutable historical record, a way to settle disputes over territory or resources by referring to past events and agreements that were literally set in wood. They preserved genealogy, recorded treaties, and noted the reigns of chiefs. In essence, the calendar stick was a library, a legal document, an agricultural almanac, and a sacred text, all rolled into one portable wooden archive. Perhaps the most captivating mystery surrounding these artifacts is the sheer diversity of their designs and the challenge of decoding them after centuries of cultural disruption. Different tribes across the continent developed their own distinct symbolic languages. A symbol that meant a successful bison hunt to a plains tribe might signify something entirely different to a Pacific Northwest tribe. This makes modern interpretation incredibly difficult, as early ethnographers often recorded the meanings from a single keeper without the full cultural context. The true, complete meaning of many surviving calendar sticks has been lost forever, as the last keepers who could read them passed away without transferring their knowledge. What remains are fragments of a beautiful and complex system, a testament to a way of knowing that viewed time not as an abstract line, but as a rich tapestry of interconnected events where the movement of a star was directly linked to the ripening of a berry, and the story of an ancestor was as important a marker of time as the solstice itself. They remind us that timekeeping is, at its core, the art of remembering, and that history can be written in many languages, even one carved patiently into a stick. Imagine an instrument so advanced that it could detect an earthquake happening hundreds of miles away, in an era when most believed such tremors were the wrath of angry gods. In the year 132 AD, during China's Han Dynasty, the brilliant polymath Zhang Heng presented the court with exactly that, an astonishing device he called the Hufeng Didongyi, or the instrument for inquiring into the wind and the movement of the earth. This was the world's first seismoscope, a large and ornate bronze urn adorned with 8 dragons, each facing a cardinal direction, and below them, 8 waiting bronze toads with open mouths. Historical accounts from the time describe its incredible accuracy, famously noting it once indicated an earthquake to the west days before messengers arrived with news of the devastation. The external design is well documented, but the true, captivating mystery lies sealed within its bronze walls, sparking a modern debate over how its internal mechanism could have possibly worked, and whether it held a secret ability to not just detect quakes, but to time them as well. The most widely accepted theory, proposed by mid-20th century researchers, suggests an ingenious pendulum-based system hidden inside the vessel. The idea is that a heavy, inverted pendulum was suspended from the top of the urn, acting as the sensitive element. When seismic waves from a distant earthquake arrived, they would cause the entire urn to sway subtly on its base. The pendulum, due to inertia, would lag behind this motion, swinging in the opposite direction. This movement would then trigger a lever or a set of gears inside the dragon corresponding to the quake's direction, releasing a bronze ball from the dragon's mouth into the waiting toad below with a loud clang. This explanation is mechanically elegant and aligns with the basic principles of physics, but it leaves a critical question unanswered. A simple pendulum mechanism would react to the initial seismic waves, but how could it distinguish the precise moment of the tremor's origin, especially if the court officials were not present at the very second the ball dropped? This is where the mystery of a potential timing element begins. This leads to a more speculative yet fascinating possibility that Zhang Heng's device incorporated a basic form of mechanical memory, a way to record the exact time of the trigger event. Some modern engineers have theorized that the internal mechanism might have been more complex than a simple lever. Imagine a system where the pendulum's swing didn't just release a ball, but also started or stopped a separate process. One compelling hypothesis involves a connection to the water clocks or clepsydras that were common in the Han court. What if the seismoscope was linked to a constant flow water source? The act of the pendulum tripping the lever could have opened a small sluice gate, allowing water to begin filling a calibrated container. The amount of water in the container when officials later discovered the alert would then indicate how much time had elapsed since the initial tremor. Alternatively, the mechanism could have stopped a constantly dripping water clock, freezing the water level at the moment of the event. This would have provided not just a direction, but a crucial temporal marker. The purpose of such timing would have been profoundly practical for the Han Imperial administration. Knowing the direction of an earthquake was valuable, but knowing precisely when it occurred could have been the key to validating the instrument's claim and mobilizing an effective response. In an empire as vast as the Han's, news traveled slowly by horse and foot. If the seismoscope sounded an alarm indicating a quake to the west, officials could check the hypothetical water level against their clepsydra logs. If it showed the event happened at the hour of the rooster, for instance, it added a layer of verifiable data to the prediction. This would help separate a genuine seismic event from a potential false alarm caused by a nearby cart rumbling past or a door slamming shut in the palace. The timing mechanism would have transformed the device from a mere indicator into a reliable scientific instrument. Its data considered trustworthy enough to launch costly disaster relief efforts to the correct province days before human messengers could arrive. Ultimately, the frustrating and beautiful truth is that we may never know the exact design of Zhang Heng's mechanism. The original device was lost to history, likely during the many conflicts that followed the Han dynasty's collapse. Later Chinese scientists attempted to recreate it, but their own records are unclear on the internal workings. Every modern reconstruction, from a 19th century Japanese model to a 2007 replica that accurately detected simulated quakes, is an educated guess based on our understanding of physics and the brief historical descriptions. The absence of a detailed blueprint is what elevates the seismoscope from a historical artifact to a timeless mystery. It stands as a powerful symbol of a scientific mind centuries ahead of its time, a reminder that the drive to measure and understand the forces of our world, to pin down not just where but when, is a pursuit that has fascinated geniuses for millennia. The true mechanism remains locked in the past, challenging us to keep searching for answers and to marvel at the fact that such profound complexity could exist inside a simple bronze urn. Long before the invention of the mechanical clock, the ancient Egyptians gazed up at the velvety night sky and saw not just a tapestry of myths, but a vast celestial timepiece of breathtaking accuracy. Their solution to measuring the hours of darkness was a system of such elegant complexity that it governed their spiritual world for millennia, the star clock or Decade system. This was far more than a simple way to tell time. It was a sacred astronomy that wove the passage of the night into the very fabric of their beliefs about life, death, and the eternal journey of the soul. Unlike a sundial which falls useless after sunset, this method turned the entire cosmos into a reliable clock, using the predictable rising and setting of 36 specific star groups, each known as a decade. The mechanics of this system reveal a sophisticated understanding of celestial motion. The Egyptians divided the sky into 36 segments, each anchored by a decade, a small constellation or a single bright star. The key to telling time was observing the heliacal rising of these stars, which is the moment a star first becomes visible on the eastern horizon just before dawn, after a period of being hidden by the sun's glare. Each decade would have its heliacal rising spaced roughly 10 days apart, making them perfect markers for tracking the 36 10-day weeks of the Egyptian civil calendar. But for telling time through a single night, they used a different observation. They would note which decade was culminating or reaching its highest point in the sky south of the zenith at the moment of twilight. As the night progressed, each subsequent decade would reach this same point roughly every 40 minutes, effectively marking the passage of an hour. This created a rolling, celestial clock face that advanced one decade each hour throughout the night. This profound knowledge was not reserved for a few elite astronomers. It was etched into the very stone of eternity itself. The earliest and most sacred evidence of the Deccan system is found in the pyramid texts, the oldest known religious writings in the world, inscribed on the internal walls of 5th and 6th dynasty pyramids dating back over 4,400 years. These spells were a guide for the deceased pharaoh's soul to navigate the afterlife, and the Deccans were his celestial roadmap. The texts name these stars and provide instructions for the king to join them, to sail with them in the solar bark of the god Ra, and to be reborn with them each dawn. The Deccans were not distant points of light. They were powerful, sentient beings, divine guardians of the night who could grant life and protection to the worthy soul. This intimate link between time, the stars, and the afterlife shows that for the Egyptians, astronomy was inseparable from theology. Within the bustling, living temples, the Deccan system took on a more practical, yet equally sacred, role in daily ritual. The Egyptian temple was seen as a microcosm of the universe, and its daily routine was meticulously designed to maintain the cosmic order, or mat. The precise timing of rituals was paramount. Priests, who are also trained astronomer timekeepers, used the Deccans to ensure that the most critical ceremonies occurred at the exact right moment. The pivotal ceremony was the Awakening of Osiris, a ritual performed in the deepest, darkest hour of the night to symbolize the resurrection of the god, and by extension, the hoped-for rebirth of every Egyptian. By observing which Deccan was culminating, the priests could know when to enter the inner sanctum, when to chant the hymns, and when to present the offerings to the god statue. The stars, therefore, did not just mark the hours, they orchestrated the divine dialogue between humanity and the gods, ensuring the rituals had their maximum efficacy and the universe remained in balance. This brings us to the central, haunting mystery of the Deccan system. How did they maintain such precise accuracy over centuries, even millennia, when the very sky they observed was slowly changing? The Earth's axis wobbles in a 26,000-year cycle called precession, which causes the positions of the stars to shift gradually over time. A star that marked the first hour of night 1 century would, a few hundred years later, rise at a completely different time. The Deccan clocks inscribed in the pyramid texts would have become obsolete within a few generations. The fact that the system remained a cornerstone of Egyptian timekeeping for thousands of years means it was not a static, rigid set of instructions, but a living science that was continuously updated and refined. This required an institutionalized tradition of observation, a dedicated class of priest astronomers who patiently recorded the slow drift of the stars across generations and made necessary adjustments to their charts and methods. They likely used other, more fixed celestial markers to recalibrate the system, such as the never-setting circumpolar stars that rotated around the North Pole. The knowledge was probably passed down through a strict oral tradition and meticulously copied and updated in temple scriptoria. The loss of this continuous, granular record, the observing logs, the corrected star tables, is what leaves the full extent of their understanding shrouded in mystery. We see the results of their work in the continuity of their rituals, but the centuries of diligent effort behind that continuity have vanished, leaving us to marvel at the sheer intellectual perseverance of a civilization that committed itself to tracking the timeless dance of the stars, all to keep their world and their universe in perfect, harmonious rhythm. From the cool, starlit temples of Egypt, we now travel to the scorching, sun-baked plains of southern Peru, where an entirely different kind of celestial mystery is etched into the very surface of the earth. Here, sprawled across nearly 200 square miles of the Pampa Colorada, lies one of archaeology's most enduring riddles, the Nazca Lines. These are not stone circles or towering monuments, but enormous geoglyphs, shallow lines scraped into the dark, iron-coated desert pavement to reveal the lighter-colored earth beneath. They form hundreds of intricate designs, from simple geometric shapes and sweeping straight lines that run for miles to spectacular figures of a hummingbird, a spider, a monkey, and even a giant astronaut. For decades, the prevailing theory was that these massive artworks could only be fully appreciated from the air, a fact that has fueled endless speculation about ancient astronauts. But a far more grounded and perhaps more fascinating theory suggests these lines were not meant for the gods above, but were instead a colossal calendar and observatory designed to map the heavens from the ground and synchronize human life with the cosmos. The sheer scale and precision of these geoglyphs is almost beyond comprehension. The straight lines are astonishingly accurate, with some stretching over 30 miles across the desert while deviating by no more than a few yards over their entire length. The animal figures, some over 900 feet long, are drawn with a single, continuous line that never crosses itself, a feat of engineering that would have required sophisticated planning and surveying techniques. The creators, the Nazca people, flourished between 200 BC and 600 AD, and they left behind no written records to explain their purpose. This silence has led researchers to look for clues in the line's relationship with the sky above them. The theory that they functioned as a giant astronomical calendar was first seriously proposed in the 1940s by historian Paul Kosok, who was conducting fieldwork near Nazca. While observing the sunset on the winter solstice in June 1941, he noticed that the sun set directly at the end of one of the long, straight lines. He famously declared the Pampa the largest astronomy book in the world, a phrase that would capture the public imagination and set the course for decades of research. This idea was passionately pursued by German mathematician Maria Reich, who dedicated her life to mapping and protecting the lines. She meticulously documented numerous alignments between the geoglyphs and key celestial events. She proposed that many of the long lines pointed toward the rising or setting positions of the sun, moon, and prominent stars and constellations during the solstices and equinoxes. For instance, one of the most famous shapes, a large trapezoid, is aligned so that its central axis points directly to the winter solstice sunrise in the southern hemisphere. Other lines appear to frame the Pleiades star cluster, which held significant importance for many Andean cultures as a marker for the agricultural calendar. The giant spider figure is often cited as a potential representation of the constellation Orion. Reich and others argued that the entire desert plain was a vast astronomical diagram where the movements of celestial bodies could be tracked by observing them in relation to these permanent terrestrial markers. This celestial theory, however, is not without its fierce critics and a compelling counter-argument. The main challenge is the sheer number of lines. With over 800 straight lines crisscrossing the Pampa, statistically, some of them are bound to align with major astronomical events simply by random chance. Skeptics argue that if you draw enough lines in enough directions, you will inevitably find a few that match the sun's position at the solstices or the position of a bright star. Furthermore, more recent and rigorous statistical analyses have failed to find a stronger correlation between the lines and astronomical events than would be expected by pure coincidence. This has led many archaeologists to propose alternative and perhaps more socially complex explanations for the line's primary purpose, moving the debate beyond a simple yes or no question of astronomy. This brings us to the heart of the modern debate. Were the lines primarily an astronomical calendar or part of a profound ritual landscape focused on water and fertility? The Nazca Desert is one of the driest places on Earth, receiving negligible rainfall. For the Nazca people, water was not just a resource, it was the literal source of life, and its scarcity would have dominated their spiritual and practical world. Many researchers now believe the geoglyphs were intimately connected to rituals designed to appease the mountain gods and ensure the flow of water from the Andes. The lines often lead to small shrines or natural sources of water, and their design may have been intended as pathways for ceremonial processions. The act of walking these lines, perhaps in a ritualistic fashion, could have been a form of pilgrimage or a prayer for rain. The figures themselves, the hummingbird, the whale, the monkey, may not be constellations but rather sacred animals associated with water, fertility, and the underworld in Nazca mythology. In this view, the astronomical alignments are not the primary purpose but a secondary, symbolic layer, connecting the life-giving power of water with the cyclical, life-giving power of the celestial bodies that govern the seasons. Ultimately, the most compelling resolution may be one that synthesizes these ideas rather than choosing one over the other. For the Nazca, the concepts of water, agriculture, and astronomy were likely inseparable parts of a single, holistic worldview. The arrival of the solstice sun was not just an astronomical event. It signaled a change in the seasons, a time to prepare for planting or harvesting. The pre-dawn rising of the Pleiades in May marked the beginning of the dry season and the end of the harvest, a critical moment in the agricultural cycle. The lines could have served all these functions at once. They were astronomical markers for tracking these vitally important dates. They were sacred pathways for rituals aimed at bringing the water those seasons required. And they were powerful social projects that united the community in a shared, monumental endeavor. The true genius of the Nazca lines may lie in this very ambiguity, their ability to function on multiple levels, practical, spiritual, and social, binding the community to the land, the sky, and each other in a continuous cycle of observance and hope. They remain a breathtaking testament to a culture that sought to inscribe its understanding of the universe onto the landscape itself, creating a permanent dialogue between the earth and the heavens. While European knights fought for earthly kingdoms, a different kind of battle for order was being waged within the silent, stone walls of medieval monasteries. Here, the most precious commodity was not land or gold, but time itself, specifically, the sacred hours of the divine office, the 8 daily prayer services that structured monastic life from before dawn until well after dusk. The call to prayer could not be left to chance or the variable sleepiness of a human watchman. It demanded a mechanical certainty that mirrored the unwavering rhythm of their faith. Their astonishing solution, emerging in the centuries before the widespread mechanical clock, was the development of sophisticated water-powered clocks, or horologia, that were marvels of early medieval engineering. These were not the simple inflow clepsydras of antiquity, but complex machines that transformed the relentless flow of water into a reliable, automated caller to prayer, achieving a level of precision that seems to defy the so-called Dark Ages. The internal mechanics of these monastic water clocks were a symphony of hydraulics and simple machines. While no complete original survives, detailed descriptions from monks like the 13th century French architect Villard de Honnecourt provide a fascinating blueprint. The core of the system was often a large, constant-level reservoir that fed water at a steady pressure into the timing mechanism. This water would drip into a receiving bucket, but the true genius was in what happened next. As the bucket filled, its increasing weight would eventually trip a sophisticated release mechanism. This could involve a chain or cord attached to a counterweight, or a pivoting lever that would suddenly release the bucket, causing it to dump its contents. This action, occurring at a fixed interval, would then drive the rest of the clock's functions. The released energy might turn a gear train connected to a dial showing the hour, or, more crucially, it would power an automaton, a striking figure of an angel or a saint that would ring a bell or strike a gong to alert the entire monastery that it was time to gather for prayers. This transformation of a constant drip into a powerful, intermittent strike was the mechanical heartbeat of the monastic day. This incredible sophistication immediately presents a profound historical puzzle. Where did this technology originate? The monasteries of 10th century Europe were not known as hubs of mechanical innovation. The most compelling theory points to a transmission of knowledge from the Islamic world, which had been refining complex water clocks like the elaborate elephant clock of Al-Jazari for centuries. Through the slow, patient work of translators in places like Moorish Spain or during the Crusades, Arabic texts on engineering and hydraulics may have found their way into monastic libraries, where mechanically minded monks adapted these designs for their own sacred purposes. Alternatively, the knowledge could be a surviving thread from the Roman era, preserved and enhanced within the isolated, stable environment of the monastery, which was one of the few institutions with the resources, continuity, and motivation to undertake such long-term engineering projects. The monastic clock was likely not a spontaneous invention, but a brilliant adaptation of Eastern or ancient knowledge, filtered through a uniquely Western Christian need for liturgical precision. The ultimate purpose of these devices was to solve a very specific and critical problem: the accurate division of the night into the canonical hours. The most challenging prayer to time was Matins, the night office, which had to be sung at a specific point in the middle of the night. A water clock that could reliably measure a 6 or 8 hour interval in the cold, dark silence of the monastery was invaluable. It freed a designated monk from the exhausting and error-prone task of staring at stars or waiting for a rooster to crow. This automation was about more than convenience, it was about spiritual discipline. By ensuring that not a single prayer hour was missed or performed late, the water clock helped maintain the unbroken cycle of devotion that was believed to sanctify time itself. The steady, rhythmic sounding of the clock's bell was an audible manifestation of the order and harmony the monastic community sought to create on earth, a mechanical echo of the celestial order they worshiped. The legacy of these monastic timekeepers is far greater than their immediate function. They represent a crucial and often overlooked bridge in the history of technology. The monks who designed, built, and maintained these intricate hydraulic machines were cultivating a practical knowledge of gears, escapements, weight drives, and automata. This hands-on expertise provided the essential foundation upon which the great mechanical clockwork of the later medieval period was built. When the first weight-driven turret clocks began to appear in European town squares in the 13th century, they were not a sudden invention but an evolution, transferring the technology of timekeeping from the sacred confines of the monastery to the secular heart of the growing city. The monastic water clock, therefore, stands as a testament to the fact that the pursuit of sacred order could, almost incidentally, give birth to the technology that would eventually regiment all of modern life. Now we venture into one of the most controversial and speculative corners of archaeology, a realm that challenges the very foundations of our historical timeline. These are the UPARTs, out-of-place artifacts, objects that seem impossibly anachronistic, their technological sophistication clashing violently with the era from which they are purported to come. Among these enigmatic finds, a few have sparked intense debate over whether they could be fragments of a lost science of timekeeping, evidence of civilizations that mastered the measurement of time in ways we can scarcely imagine. The most famous of these, and perhaps the most hotly debated, is the curious case of the Koso artifact, a discovery that seems to defy any easy explanation and plunges us headlong into a mystery that pits mainstream archaeology against tantalizing fringe possibilities. The story begins in 1961 when 3 rockhounds were hunting for geodes on a peak near Olancha, California. After cutting open what appeared to be a perfectly ordinary lump of hardened clay, they were stunned to find not the expected crystal cavity, but a mechanical-looking object embedded firmly inside. The item consisted of a porcelain or ceramic cylinder with a 2mm metal shaft running through its center. The shaft was magnetic, and the cylinder was surrounded by a hexagonal layer of hardened clay and pebbles, which itself was encased in a shell of fossilized shells and what appeared to be an iron cone. The men were convinced they had found some kind of ancient spark plug, but the geology told a far more incredible story. The nodule was found in a stratum that geologists dated to over 500,000 years old, a time when, according to conventional history, the most advanced creature on Earth was Homo erectus. If the dating was correct, this object had no business being there. This is where the mystery deepens into a classic UPART conundrum. skeptics and mainstream archaeologists quickly offered a more mundane explanation. Upon closer inspection, the object was identified by some as a 1920s-era champion spark plug, a common part for Model T Fords. The theory is that the spark plug fell to the ground, perhaps from a passing vehicle, and over the decades, minerals like iron oxide and calcium carbonate concreted around it, creating a hard, geode-like nodule that simply looked ancient. This process, known as concretion, can happen surprisingly quickly under the right conditions, creating a rind that mimics a much older geological formation. For most scientists, this case was closed, a classic example of misidentification and the power of natural processes to create seemingly impossible objects. Yet the controversy has never fully died, and the questions it raises are profound. If it is a spark plug, why was the surrounding matrix so incredibly hard and seemingly ancient? The original finders insisted the object was fully encased and had to be broken out, a claim that challenges the idea of a rapid concretion. More intriguingly, some researchers have pointed to the object's unique design, noting that its specific configuration doesn't perfectly match any known spark plug model from the era. This sliver of doubt is what fuels the alternative theory, that the Koso artifact is a genuine relic of a hyper-advanced prehistoric civilization, perhaps even visitors from another world. In this view, the object's cylindrical and hexagonal components could be part of a sophisticated, unknown technological device. Could it have been a component of an ancient energy source, or perhaps even part of a complex timekeeping mechanism that used magnetic fields or crystalline vibrations to measure intervals with incredible precision? The magnetic metal shaft and the ceramic insulator are elements found in modern electronics, leading some to speculate about its potential function in a lost system of technology. The Koso artifact is not alone in this strange category. Other alleged parts, like the Antikythera Mechanism was before it was understood, are often pointed to as potential evidence of lost timekeeping tech. The Dorchester pot, a metallic vase allegedly dynamited out of solid rock in the 1800s, featured intricate silver inlay and was suggested by some to be an ancient capacitor or energy cell, though it has since been lost and its story is likely a hoax. The question these objects collectively pose is not necessarily whether they are proof of aliens, but whether we have been too quick to dismiss the possibility of isolated pockets of advanced knowledge in the ancient past. Could a culture have developed a unique, mechanical understanding of time that was later completely lost, its only traces being these bizarre, misinterpreted fragments that we now dig up and call parts? Ultimately, the mystery of the Koso artifact and its kin is a powerful lesson in the scientific process and the human desire for mystery. It forces us to confront the limits of our knowledge and the reliability of our dating methods. It highlights the importance of Occam's razor, the principle that the simplest explanation is usually the correct one, while simultaneously reminding us that history is often far more complex and surprising than our textbooks allow. Whether a misidentified spark plug or a genuine enigma, the Koso artifact serves as a permanent question mark, a challenge to our linear view of progress. It dares us to keep an open mind, to question our assumptions, and to wonder if, buried deep within the strata of our planet, there might lie evidence of other ways to measure the eternal, relentless flow of time. For a civilization surrounded by the endless blue of the Pacific Ocean, the ability to navigate was synonymous with survival itself. The Polynesian voyagers who settled the most far-flung islands on Earth faced a navigational challenge unlike any other, crossing thousands of miles of open water without compasses, maps, or sextants. Their solution was a breathtakingly sophisticated form of time-space reckoning that used the heavens not as a clock, but as a compass, a calendar, and a roadmap all woven into one. This was not a system of gears or monuments, it was a living science carried in memory, a celestial knowledge so precise it could guide a canoe from Tahiti to Hawaii, a journey of over 2,500 miles with pinpoint accuracy. The mystery is not just how they did it, but how they perfected this art in total isolation, developing a concept of time that was intrinsically linked to movement and memory across the vastest expanse on the planet. At the heart of this system was the star compass, a mental construct that divided the horizon into 32 houses, each named for a star or constellation that rose and set in that specific quadrant. A master navigator, or PWO, didn't just know the names of these stars, he knew the entire star path, the sequence of stars that would rise in succession throughout the night as his canoe sailed on a constant bearing. He would steer by keeping the rising point of a specific star directly off the bow or stern of the canoe. As that star climbed too high to be useful or set beneath the horizon, he would immediately transition to the next star in that same house's path, maintaining his course through the continuous, rhythmic dance of the celestial sphere. This required an incredible mental model of the sky's rotation, a kind of astronomical clockwork held entirely in the navigator's mind, allowing him to hold a steady course for weeks on end without any visible landmarks. But the stars were only part of the story. The true genius of Polynesian navigation lay in reading the ocean itself, an art that turned the sea from a featureless void into a textured, readable map. Navigators learned to interpret the deep, rolling ocean swells, the wave trains that travel great distances from consistent weather systems. They could feel the specific rhythm and direction of these swells through the roll of their canoe, using them as a constant directional guide that persisted even when the sun was high and the stars were invisible. They observed the subtle deflection of these swells as they wrapped around islands, sensing land long before it was visible. They memorized the specific bird species that flew out to sea to feed at dawn and returned to land at dusk, using their flight paths as living arrows pointing toward invisible shores. This multidimensional awareness created a fail-safe system. If clouds obscured the stars for a night, the swells would guide them. If the sea was calm, the birds and the sun's zenith would provide the clues. It was a robust, redundant natural GPS system built from generations of accumulated observation. This profound knowledge was not written down but preserved through an intricate and powerful oral tradition. The entirety of this navigational science, the star paths, the swell patterns, the sequences of island discoveries, was encoded into chants, songs, and stories. These were not simple mnemonics, they were intricate oral maps where a single verse could contain the sailing directions for an entire archipelago. A chant might name a series of stars in the order they would be used on a voyage, or describe the feeling of specific wave patterns against the hull. Young navigators in training, often from childhood, would spend years memorizing these chants and practicing their craft on short voyages, gradually learning to translate the poetic phrases into real-world sensory input. The rhythm of the chant itself mirrored the rhythm of the voyage, embedding the timing and sequence of the journey into the very structure of the memory aid. This was how 1,000 years of exploratory history and celestial observation was faithfully transmitted from one generation to the next, ensuring that the pathways between islands, some separated by hundreds of miles of open ocean, remained open and known. This intricate understanding of the heavens and the seas was perfectly synchronized with the rhythms of nature, creating a calendar for seasonal migration. The Polynesians were not just random explorers, they were deliberate settlers and traders who timed their long-distance voyages with the shifting seasons and the predictable behavior of marine life. The appearance of certain stars on the horizon at dusk or dawn signaled the arrival of specific seasons. The rising of the Pleiades cluster, known as Matariki in Maori or Makali in Hawaiian, marked the beginning of the new year and the start of the prime season for long-distance voyaging, as it coincided with the period of more predictable winds and calmer seas. This celestial event told them it was time to launch the great double-hulled canoes, the Waikolua, to transport people, goods, and even entire families to different islands for trade, marriage, or seasonal resource gathering. Their calendar was not a list of dates on a wall, but a dynamic set of environmental and celestial cues that dictated the most opportune and safest times to engage in the most dangerous and important activity their culture knew, connecting their widespread island nation across the timeless sea. While the monasteries of Europe were meticulously measuring the hours for prayer with their water clocks, a brilliant light of scientific inquiry was burning even brighter in the heart of the Abbasid Caliphate. In 9th century Baghdad, the House of Wisdom, or Beit al-Hikmah, was not just a library but a vibrant epicenter of innovation, a place where scholars from across the known world gathered to translate, debate, and advance human knowledge in every field, especially astronomy. Here, the quest to measure time was driven by a powerful need for religious precision, determining the 5 daily prayer times and the direction of Mecca, or Qibla, from any location. But it soon blossomed into a scientific revolution that would produce some of the most sophisticated timekeeping devices the world had ever seen. This was the Islamic Golden Age, and its horological advancements were so profound that their eventual loss constitutes one of history's most devastating intellectual tragedies. The mastermind behind many of these inventions was the legendary Banu Musa brothers, Ahmad, Muhammad, and Al-Hassan. These 3 polymaths, funded by the Caliphate itself, were mechanical geniuses who authored the Book of Ingenious Devices, a work that detailed an astonishing array of automata and complex machinery. Their most significant contribution to timekeeping was the refinement of the water clock, which they elevated to new heights of complexity and spectacle. They designed clocks that were not merely timekeepers but full-scale theatrical performances. Imagine a complex series of gears and valves powered by a constant flow water system. At the top of each hour, these mechanisms would trigger a dazzling display. Doors would fly open to reveal statues of human figures, musical automata would play flutes and cymbals, and precisely weighted balls would drop onto cymbals to sound the hour. One of their most famous designs even featured a model elephant with a mahout and a serpent that would move in a complex cycle, all designed to mark the passage of time with a grandeur that matched the empire's intellectual ambition. Yet the true pinnacle of this era is embodied by the magnificent elephant clock, designed by the great inventor Ismail al-Jazari in the early 13th century. This masterpiece was the culmination of centuries of Islamic engineering, a breathtaking synthesis of cultural exchange and mechanical genius. Standing as a physical testament to the vast reach of the Islamic world, the clock incorporated a Chinese dragon, an Indian elephant, Persian carpets, Egyptian phoenixes, and Arabian robotic figures, all working in harmonious concert. Its operation was a marvel of hydraulics. A water tank hidden within the howdah on the elephant's back contained a float with a small hole. As water slowly dripped into the float over a 30-minute interval, the float would sink, pulling a cord that triggered a chain reaction. This would cause a ball to drop from the falcon above into the mouth of the serpent below, whose weighted head would then tilt forward, pulling the float back to the surface and tipping the howdah to release the ball into a vase, simultaneously triggering the driver automaton to strike a cymbal. This entire complex cycle was not just a clock, it was a global symbol of knowledge and a metaphor for the universal and cyclical nature of time itself. The instruments developed for celestial timekeeping were equally advanced and even more precise. In the observatories of Baghdad, Marrakech, and Samarkand, astronomers like al-Battani and al-Sufi made painstakingly accurate observations that refined the Ptolemaic model of the universe. To do this, they invented and perfected a suite of massive, precision brass instruments. The most iconic was the astrolabe, a handheld brass computer that could solve problems of time, distance, and celestial position. But they went far beyond this, creating the mural quadrant, a giant graduated arc fixed to a wall to measure the altitude of stars with incredible accuracy. and the torquetum, a complex observational device that could convert measurements between different astronomical coordinate systems. These weren't just tools for prayer times. They were used to compile vast astronomical tables like the Tolden tables and the Handy tables, which corrected star catalogues and calculated the length of the solar year with a margin of error measured in seconds. This data was the bedrock of timekeeping, allowing for the creation of highly accurate calendars and the prediction of celestial events years in advance. This flourishing of knowledge, however, was not destined to last. The slow decline began with internal political fragmentation, but the death blow came from external invaders. The Mongol siege of Baghdad in 1258, led by Hulagu Khan, was a cataclysm from which the Islamic scientific world never fully recovered. The House of Wisdom was utterly destroyed, its libraries thrown into the Tigris River in such numbers that historians said the water ran black with the ink of books and red with the blood of scholars. While some knowledge was preserved in the surviving observatories further east, the relentless, institutionalized drive for innovation that characterized the House of Wisdom was shattered. The meticulous craft of building and maintaining these complex mechanical clocks, which required a stable, wealthy, and intellectually curious patronage, largely faded away, and the secrets of the most advanced devices were lost, surviving only as descriptions in a handful of manuscripts that themselves were scattered and forgotten for centuries. The tragedy of this loss is compounded by the profound influence these innovations eventually had on the Western world. In the centuries following the destruction of Baghdad, as Europe began its slow climb out of the Middle Ages, it was through contact with the remaining centers of Islamic learning in places like Al-Andalus in Spain and Sicily that this preserved knowledge began to filter back. European scholars eagerly translated Arabic texts on mechanics and astronomy. The very concept of the weight-driven mechanical clock, which would come to define the European late Middle Ages and Renaissance, is now widely believed by historians to have been inspired by translations of the works of the Banu Musa brothers and Al-Jazari. Their designs for complex gear trains, escapements, and automata provided the essential blueprints that European clockmakers would later adapt and simplify. The great astronomical clocks that began to appear in European cathedrals and town squares in the 14th century, with their procession of apostles, crowing roosters, and rotating celestial spheres, are the direct, albeit simplified, heirs of the magnificent water clocks that once delighted the courts of Baghdad. The House of Wisdom's legacy was not completely erased. It was merely transplanted, its seeds taking root in a different soil to eventually bear fruit in a new age, a silent and mostly forgotten bridge between the ancient world and our modern one. Standing proudly in the shadow of the Acropolis, the Tower of the Winds presents a puzzle of architectural harmony and multifunctional genius. Built in the 1st century BC by the Macedonian astronomer Andronicus of Syrtis, this beautiful octagonal marble tower, also known as the Horologion, is often called the world's first meteorological station and public timekeeping center. Its very design is a masterclass in integrating diverse scientific instruments into a single, cohesive structure, each face of its 8 walls addressing a different aspect of understanding and measuring the natural world. The tower's strategic placement in the Roman Agora, the bustling heart of Athenian commerce and social life, suggests it was built not for private scholars but for the everyday citizen, a public utility designed to bring order and information to the chaotic flow of city life. Its survival for over 2,000 years is a testament to the robustness of its construction and the timelessness of its purpose. Each of the tower's 8 sides is precisely aligned to face one of the 8 principal winds of Greek mythology, a feature that gives the building its common name. But these are not mere decorative carvings. Sculpted in high relief at the top of each wall is a magnificent figure personifying each wind, from Boreas the north wind, shown as a bearded man blowing a conch shell, to Zephyrus the gentle west wind, depicted as a youthful figure scattering flowers. This architectural choice reveals a world view where time, weather, and direction were deeply intertwined. More than just a charming motif, this alignment was fundamentally practical. By orienting the building so precisely to the compass points, Andronicus created a perfect framework for the sophisticated sundials that graced each of the 8 walls below the wind figures. These were not simple, generic dials. Each one was custom designed for the specific angle of the sun it would receive on its particular wall, allowing for incredibly accurate solar timekeeping throughout the entire day as the sun moved across the sky. The tower's timekeeping capabilities, however, did not vanish with the setting sun. This is where the design reveals its true brilliance as an all-weather, round-the-clock time station. Ancient sources and archaeological evidence suggest the tower also housed a substantial water clock, or clepsydra, inside its walls. This was likely a complex system that used a constant flow of water to power a mechanism indicating the hours. The genius of the horologian's design lies in the seamless integration of these two systems. The sundials provided the most accurate solar time during daylight hours, and it is highly probable that this solar time was used to regularly calibrate and adjust the water clock. This would counteract the inherent drift and inaccuracies that could accumulate in a clepsydra over time, ensuring that even on cloudy days or through the night, the tower displayed a time that was synchronized with the solar day. It was a continuous feedback loop of timekeeping, a mechanical brain that could self-correct. Perhaps the most striking feature, and the one that cemented its role as a full meteorological station, was the bronze weather vane that once graced its roof. At the very summit of the tower stood a bronze figure of Triton, the sea god, who pivoted to point his rod in the direction of the prevailing wind. This was not a simple decorative flourish. For a maritime trading power like Athens, knowing the wind direction was critical economic and travel information. A sailor planning a voyage could consult the tower to understand the weather conditions, while merchants could use it to predict the arrival of ships. The weather vane's placement atop the timekeeping structure powerfully illustrates the ancient Greek understanding that time and weather are inseparable forces governing human activity. The tower didn't just tell you what hour it was, it told you what the hour meant for your plans. This convergence of functions leads us to the central question of its public role. How did this integrated data reach the people of Athens? The tower was almost certainly designed for easy public reading. The sundials on its exterior walls were large and clearly marked, visible to any passerby. We can imagine the water clock inside driving an external display, perhaps a series of pointers on a large dial or even an automaton that would mark the hours audibly. The turning Triton on the roof was a massive, visible signal for the entire agora. The horologion was therefore far more than a scientific curiosity. It was the city's central timepiece and weather station, a hub of practical information that regulated commerce, legal proceedings, social appointments, and travel. It brought the abstract concepts of horology and meteorology down to the street level, making advanced scientific knowledge a democratic tool for every Athenian citizen, a timeless symbol of public science serving the common good. Moving from the sunlit public squares of ancient Greece, we now venture into the misty forests of Iron Age Europe, where a different kind of timekeeping mystery was being forged in bronze. The Celts, often mistakenly characterized as wild barbarians by their Roman contemporaries, left behind a stunning artifact that reveals a mind-bendingly complex understanding of the cosmos, the Coligny calendar. Discovered in 1897 in Coligny, France, this fragmented bronze tablet is the most significant ancient Celtic calendar ever found. A 5-foot-long, intricate puzzle of holes, numerals, and Gaulish words that has taken scholars over a century to even begin to decipher. It's not just a list of days, it's a monumental, hybrid timekeeping system that attempts to reconcile the stubborn mismatch between the sun's year and the moon's month with a sophistication that rivals anything produced by the Mediterranean powers of the era. The core structure of the Coligny calendar is a magnificent, if complex, dance between the moon and the sun. At its heart, it is a lunisolar calendar, meaning it tracks both the lunar months and the solar year. The calendar is organized into 5 great cycles, each spanning 62 lunar months, which comes incredibly close to aligning with 5 solar years. Each year is then divided into 12 lunar months, but here's where the Celtic ingenuity truly shines. A lunar month is only about 29.5 days long, which doesn't divide neatly into a whole number of days. The creators of the Coligny calendar solved this with a brilliantly simple notation. Each month is alternately 29 or 30 days long, a system still used in some modern lunar calendars. But they didn't stop there. To keep this lunar year in sync with the true solar year of 365.25 days, they periodically inserted an entire extra month. This intercalary month, called Sonosingos, was added every 2.5 years, a correction that required incredibly precise long-term astronomical observation to calculate and implement. What truly sets the Coligny calendar apart and imbues it with deep mystery are the markings themselves. The days are not just numbers, they are a cryptic code of abbreviations. Each day is marked with one of 2 words, mat or annum. For a long time, these were thought to be simple good and bad days, perhaps for divination. However, more recent interpretations suggest they might indicate something far more nuanced, whether the day was considered lucky or unlawful for certain social, legal, or religious activities. A day marked Einem might have been a day when court rulings were suspended, contracts couldn't be signed, or specific rituals were forbidden. This transforms the calendar from a mere time tracker into a social and religious regulator, a framework that dictated the rhythm of public life, law, and worship, all based on a perceived cosmic order. This brings us to the most perplexing and debated feature of the entire system, the mysterious 5-day weeks. The calendar clearly shows a division of each month into 2 halves. But within this structure, scholars have identified recurring 5-day periods that simply don't align with our modern 7-day week. These enigmatic cycles have no obvious parallel in other contemporary calendars. Were these 5-day blocks a unit of work like a market cycle? Could they represent a religious period, a time set aside for specific ceremonies or observances that occurred every 5th day? Or were they perhaps an abstract mathematical device, a convenient way for the Druid astronomers to perform their complex calculations for inserting the intercalary months and predicting lunar phases? The lack of any written Celtic explanation leaves this as one of the most tantalizing open questions, a glimpse into a completely different way of segmenting and perceiving the flow of time. The purpose of such a complex public calendar speaks volumes about the structure of Celtic society. This was not a private document for priests alone. The fact that it was made of durable bronze and inscribed with such care suggests it was a public-facing monument, likely displayed in a sacred grove or a chieftain's hall. It would have been the ultimate authority for settling disputes over contracts, for knowing when taxes were due, for scheduling major festivals like Samhain and Imbolc, and for mustering warriors. The Druids, the intellectual elite of Celtic society, were almost certainly its creators and guardians. Their ability to create and maintain this system was a profound source of power. By controlling the calendar, they controlled the very rhythm of life, demonstrating a connection to the divine order that legitimized their authority. The Coligny calendar is thus far more than a timekeeping device. It is a powerful political and religious statement cast in bronze, a testament to a sophisticated European civilization whose deep understanding of time was written in a language we are still struggling to fully understand. Venturing now into the very cradle of humanity, we find evidence of our species' first attempts to impose order on the passage of time, not carved in stone or forged in metal, but painted with ochre and charcoal on the sacred canvas of cave walls. Across the vast expanse of Africa, from the sun-scorched Sahara to the verdant south, ancient rock art does far more than depict majestic animals and human figures. It appears to encode a deep understanding of natural cycles, acting as a monumental calendar painted by the very first timekeepers. These are not the precise instruments of later empires, but something perhaps more profound: the nascent human impulse to track, predict, and find meaning in the rhythm of the world, blending acute observation with a burgeoning spiritual consciousness. Some of the most compelling evidence comes from sites like the Apollo 11 cave in Namibia and the Linton Panel in South Africa, where paintings and engravings are thought to be among the oldest in the world, dating back tens of thousands of years. Here, researchers have noted fascinating patterns. Certain animal species are depicted in specific poses or in association with particular symbols only at certain times of the year. A pregnant antelope might be shown near a cluster of dots that could represent a star cluster, or a herd of elephants might be painted following a line that mirrors the path of the sun on the horizon during the rainy season. This is not random decoration. It suggests a meticulous, generational recording of which animals were present, migrating, or giving birth during specific seasons, creating a visual almanac that was crucial for survival. The art was a database, a way of passing down essential ecological knowledge from one generation to the next, ensuring that hunting parties knew when and where to find prey and when certain plants would be in fruit. This practice of tracking was not limited to biological cycles. At a site in modern-day Chad, a fascinating series of engravings shows what appears to be a series of tally marks grouped in sequences that correspond to lunar phases. Another panel in Tanzania features a human figure with upraised arms, positioned so that during the summer solstice, a shaft of sunlight pierces a crack in the cave roof to illuminate it perfectly. These are not isolated incidents. They are repeated patterns that point to a widespread Paleolithic understanding of celestial mechanics. Without written language, these early artists used the most permanent medium they had, the rock face itself, to mark the solstices, equinoxes, and the wandering path of the moon, turning entire landscapes into enormous natural observatories. The cave was their planetarium, and the pigments their equations. This leads to the profound cultural question at the heart of this mystery: what was the ultimate purpose of encoding this knowledge in art? For these early communities, the line between the practical and the spiritual was undoubtedly blurred. Knowing when the rains would come was a matter of life and death, and that knowledge was too important to be left to chance or vague memory. By ritualizing it in art, they were perhaps performing a kind of sympathetic magic, a way of ensuring the return of the herds and the seasons by depicting it on the wall. The shaman or artist who painted the antelope was not just recording a food source. They were perhaps capturing its spirit, invoking its return for the next season. The calendar was therefore also an altar, a place where the community could gather to synchronize their rituals with the cosmic and ecological cycles, reinforcing social bonds and affirming their place in a vast, interconnected world. The true wonder of these ancient galleries is the window they provide into the dawn of human cognition. Developing these seasonal markers required a colossal intellectual leap, the ability to observe a pattern, remember it across seasonal cycles, predict its recurrence, and then create a symbolic representation of that prediction for others to understand. This is the foundation of science, art, and religion, all emerging simultaneously from the same creative act. It represents a shift from simply reacting to the environment to actively seeking to understand and influence it. These first timekeepers were mapping time itself onto space, creating a permanent record of impermanent events, and in doing so, they were laying the foundational stones for all the sophisticated calendars and clocks we would later invent. In the flickering torchlight of those deep caves, they weren't just painting animals. They were trying to tame the relentless flow of time, to make it tangible, predictable, and sacred. High in the lush canopy of the Yucatan Peninsula, A peculiar, snail-shaped tower rises above the ancient Maya city of Chichen Itza, its stark geometric form a startling contrast to the massive stepped pyramids below. This is El Caracol, the snail, named for the spiral staircase that winds within its central tower, and it stands as one of the most architecturally unique and enigmatic structures in the entire pre-Columbian world. Unlike the grand temples dedicated to gods and kings, El Caracol's purpose seems purely cerebral, a sophisticated observatory designed to track the complex dance of planets and stars with a precision that seems to defy its ancient origins. Its design is a masterpiece of intentionality. The entire building is cocked at a curious angle, its main platform not aligned with the other structures in the complex, a clear signal that its architects were orienting it towards something far more specific than the cardinal directions. This was not a place of vague celestial wonder. It was a functioning laboratory for hard science, a stone computer dedicated to calculating the rhythms of the cosmos. The true genius of El Caracol is revealed not in its overall shape, but in the meticulously placed slits and apertures in its upper tower. These are not random windows or decorative features. They are precisely engineered sightlines, stone gun barrels aimed at key points on the horizon. From the darkened interior of the observatory chamber, a Maya astronomer priest would have peered through these narrow openings, using them to frame the rising and setting of specific celestial bodies against the distant, flat jungle canopy. One famous alignment is directed toward the extreme northern setting of Venus, while another captures its southernmost rise. Other slits are believed to have framed the solstice sunsets and the equinox sunrises, creating a permanent, fixed grid against which the sky's movements could be measured with incredible accuracy. The building itself was the instrument, its immovable stone walls providing a constant reference point that allowed for the detection of the most subtle shifts in a planet's position over long periods. This architectural approach to astronomy turned the entire horizon into a calibrated dial, with the observatory as its fixed central pointer. This architectural precision was dedicated to a single, overpowering celestial obsession, the planet Venus. In Maya cosmology, Venus was not a benign point of light. It was the avatar of the god Kukulkan, known as Quetzalcoatl to the Aztecs, a deity associated with both creation and violent upheaval. Its movements were seen as profoundly ominous, directly influencing the timing of warfare, the coronation of kings, and major agricultural cycles. The Maya tracked the planet's 584-day synodic period, the time it takes to complete one full cycle of visibility as both the morning and evening star, with an accuracy measured in mere hours over centuries. Their calculated length for the Venus cycle was so precise that it varies from the modern measurement by only 2 hours in 584 days, a margin of error of less than 1/100th%. This staggering accuracy was not achieved through simple counting. It required a deep understanding of mathematics to correct for the slight discrepancies that would accumulate over multiple cycles, a process of long-term calibration that speaks to generations of meticulous record-keeping. This immediately raises the haunting question that hangs over all Mesoamerican astronomy. How did they achieve this naked eye precision without any form of optical enhancement? The answer lies in a relentless, institutionalized program of observation. Maya astronomer priests were civil servants of the cosmos, likely working in shifts to maintain a continuous vigil of the night sky from buildings like El Caracol and from simpler wooden observation platforms. They used simple yet effective tools like cross sticks to measure the altitude of stars as they crossed the meridian, or they would line up celestial bodies with notches on the horizon carved into distant buildings or natural landmarks. Their most powerful tool, however, was patience. They observed these cycles across generations, recording their data in intricate bark paper codices filled with complex glyphs and numbers. This long-term dataset allowed them to identify patterns and make incredibly accurate predictions, turning raw observation into predictive science. The observatory was the fixed point that anchored this centuries-long project, a permanent stone guarantee that the data collected by one generation could be reliably used by the next. The ultimate purpose of this celestial tracking extended far beyond mere scientific curiosity. It was the very engine of Maya statecraft and religion. The movements of Venus were believed to directly influence the outcome of battles. Military campaigns were meticulously planned to coincide with the first appearance of Venus as the morning star, a time when the god Kukulkan's power was considered most potent and auspicious for launching attacks. The infamous Venus pages of the Dresden Codex, one of the few surviving Maya books, are essentially a divination manual for war, outlining which phases of the Venus cycle would bring victory and which would bring defeat. But the influence went deeper than warfare. The entire ritual calendar, a 260-day cycle known as the Tzolk'in, was interlocked with the solar year and the Venus cycle in a grand, complex gearwork of time. The completion of these major cycles was a time of immense spiritual significance, requiring specific ceremonies to ensure the cosmic order continued and the gods remained benevolent. The observatories, therefore, were not just scientific instruments. They were listening posts to the divine, allowing the Maya to synchronize their entire society, its wars, its harvests, its ceremonies, and its kings with the perceived heartbeat of the universe itself. In the silent stone corridors of El Caracol, we find not primitive stargazers, but brilliant scientist priests who used architecture, mathematics, and generations of disciplined observation to weave human destiny into the very fabric of the cosmos. Consider the baffling ingenuity of a society that devotes immense skill to building a precision sundial in a place where the sun vanishes for months at a time. This is the central puzzle of ancient sundials discovered in some of the most climatically hostile locations on Earth, far from the sunny Mediterranean shores where we expect such technology to thrive. Take, for instance, the Roman sundial found at the remote fort of Vindolanda in northern Britain, a region famously known for its overcast skies and rainy weather. Or even more extreme, consider the portable sundials carried by Roman officials stationed along the gloomy Rhine frontier. Why would a culture renowned for its practicality invest such effort in a technology that seems so utterly unsuited to its environment? The answer reveals a fascinating story of necessity, adaptation, and a deep-seated human need to impose order on chaos, no matter the circumstances. These devices found in unlikely places were not simple, off-the-shelf imports from sunnier climates. They were often specially adapted for their challenging new homes. In northern latitudes, where the sun hangs low in the sky for much of the year, a standard horizontal sundial would be useless for large portions of the day, its gnomon casting a long, faint shadow that is difficult to read accurately. To solve this, we see the development of the spherical sundial, or hemicyclium, which was often mounted on a vertical surface facing south. Its concave, bowl-shaped design, etched with curving hour lines, was far better at capturing the low-angle light of a northern winter, providing a clearer and more usable shadow throughout the shortened days. Other adaptations were more practical. In windy locations, sundials were made heavier and sturdier, with shorter, thicker gnomons less likely to bend or break. Some portable models even included built-in compasses and sophisticated adjustable gnomons, allowing a traveling official to calibrate the dial for the specific latitude of their posting, a clear indication that these were precision tools for experts, not decorative trinkets. This level of customization immediately forces a deeper question about their purpose. If the weather was so frequently poor, how could a sundial possibly have been a reliable daily timepiece? The key is to rethink our modern expectation of constant, minute-by-minute timekeeping. In the ancient world, the primary purpose of a sundial was not to tell the time to the exact minute for a coffee break, but to mark the broader, more important divisions of the day. The canonical hours for prayer in a monastery, the changing of military watches at a fort, or the appointed hour for a legal proceeding or market to open in a town. On a bright, sunny day, the sundial provided the most accurate reference available. On an overcast day, life simply proceeded according to routine and the rough estimate of experienced individuals. The sundial was the authority that reset the community's internal clock whenever the sun deigned to appear, correcting the accumulated drift of guesswork and ensuring that a watch change at a remote fort in Scotland was synchronized in principle with the rhythm of the empire itself. Beyond the practical, the presence of these sundials in harsh environments speaks to a powerful psychological and cultural imperative. For a Roman soldier stationed at Hadrian's Wall, 1,000 miles from home, the sundial was far more than a tool. It was a potent symbol of Roman order and civilization. Erecting a precisely engineered sundial in the misty wilderness was an act of defiance against the chaos of the unknown. It was a statement that here, too, Roman law and Roman time prevailed. It connected that lonely soldier through the shared language of hours and seasons to the heart of the empire. The sundial was a tiny piece of home, a mechanical comfort that replicated the familiar rhythms of the Roman day in a foreign and often hostile land. Its very existence, even when shrouded by fog, was a promise that the sun of Rome would not set on this outpost, reinforcing the identity and discipline of the men who guarded the edge of the known world. Ultimately, these sundials stand as a testament to the adaptability and determination of ancient engineers. They refused to be limited by their environment, instead innovating and refining their designs to meet the challenge. A sundial in the far north is a paradox that only a brilliant and stubborn mind could resolve. It represents a refusal to surrender to the darkness, a commitment to measurement and order even when nature seems to conspire against it. These artifacts remind us that the human drive to understand and quantify our place in the cosmos is not dependent on perfect conditions. It flourishes everywhere, from the sun-baked temples of Egypt to the rain-lashed stone walls of a distant frontier fort, proving that the need to mark time is as fundamental to the human spirit as the need for shelter or food. Imagine a single institution so vast it aimed to collect all the knowledge in the known world. A place where the greatest minds of antiquity gathered not just to preserve existing ideas, but to push the boundaries of science and mechanics into realms that would not be seen again for over 1,000 years. This was the legendary Library of Alexandria, the intellectual crown jewel of the Ptolemaic dynasty in Egypt, and within its hallowed halls, the science of timekeeping may have reached a peak of sophistication that history has almost completely forgotten. The library and its associated Mauseon, a grand research institute, were more than a storage house for scrolls. They were a dynamic engine of innovation, funded by the state to pursue pure research and applied engineering. It was here that geniuses like Ctesibius, the father of pneumatics, and Hero, the master of automata, are said to have designed devices of such stunning complexity that their loss represents one of the most devastating voids in our understanding of ancient technology. The accounts that have trickled down through time are not of simple water clocks, but of mechanical marvels that seem to leap centuries ahead of their time. The most tantalizing glimpses come from the work of these brilliant engineers, whose inventions were documented in texts that themselves were later lost, surviving only as references in the writings of others. Ctesibius, who worked in Alexandria in the 3rd century BC, is credited with a revolutionary improvement to the clepsydra. He understood the fundamental flaw of water clocks, that the flow of water slows as the supply tank empties, and his ingenious solution was the constant level tank, an intermediary reservoir with an overflow siphon that maintained a perfectly steady water pressure. But he didn't stop there. Historical accounts suggest he used this regulated flow to power an entire symphony of automation. His clock allegedly featured a floating figure that rose to point at the hour on a graduated scale, ringing bells, moving miniature statues, and even causing birds to sing on the hour. This was not just a timekeeper, it was a theatrical performance designed to display the power of human ingenuity and the divine order of the cosmos, all driven by the precise mathematical flow of water. Building on this foundation, the later inventor Hero of Alexandria in the 1st century AD described devices that border on the magical. In his works, we find plans for mechanisms powered by steam, water, and compressed air that could open temple doors automatically, power mechanical puppets to perform plays, and create self-regulating systems. While not all were explicitly for timekeeping, the principles are unmistakably those of advanced mechanics, gearing, feedback control, and programmable sequences. It requires only a small imaginative leap to see how these principles could have been applied to the problem of measuring time. Could Hero or one of his colleagues have created a mechanical clock using a complex gear train, driven by a falling weight or a steady water flow and regulated by an early form of escapement? The intellectual climate was certainly ripe for it. The Antikythera Mechanism, a device of comparable complexity, proves that the Greeks possessed the metallurgical and mathematical skill to create intricate geared computers. The Library of Alexandria, with its concentration of resources and talent, was the one place where such a technology could have been developed, refined, and documented on a grand scale. This leads us to the heart of the mystery and the source of our profound frustration: the complete and total loss of this potential knowledge. The library's destruction was not a single, catastrophic event, but a long, agonizing decline over centuries, a death by 1,000 cuts. The Great Fire, allegedly started by Julius Caesar in 48 BC, likely damaged the warehouse district where many scrolls were stored, but the institution struggled on. It suffered from a withdrawal of royal patronage, purges of intellectuals, and religious edicts that targeted pagan knowledge. The final blow is often attributed to the Muslim conquest of Alexandria in the 7th century, with the Caliph Omar famously, and perhaps apocryphally, declaring that if the library's contents contradicted the Quran, they were blasphemous, and if they agreed, they were superfluous. Whatever the exact sequence, the result was the same: the utter annihilation of a collective intellectual legacy. The scrolls containing the detailed diagrams of Ctesibius's clocks, Hero's automata, and the astronomical theories of Aristarchus were burned, used as fuel for baths, or simply left to rot, erasing an entire lineage of mechanical thought. The magnitude of this loss is almost incalculable. Without the Library of Alexandria as a continuous repository, this nascent technology of precise mechanical timekeeping had no incubator, no means to be passed down and incrementally improved upon by subsequent generations. The foundational work had to be rediscovered from scratch more than a millennium later in medieval Europe. One can only wonder how the course of human history might have changed if the mechanical clock, a device that would later regiment and accelerate all of European society, commerce, and science, had been allowed to evolve continuously from its Alexandrian origins. Would the scientific revolution have happened 1,000 years earlier? Would navigation and exploration have advanced at a dramatically different pace? The library's collection was a chain of knowledge, and its breaking meant a dark age for technology, a reset button pressed on human progress. The mystery of its lost timekeeping devices is therefore a haunting story of a road not taken, a glimpse of an alternate history where the tick of a mechanical clock might have echoed through ancient streets, a sound that the world would not hear again until the spires of Gothic cathedrals began to ring with the chimes of a new age, born from the ashes of a forgotten one. Now, after exploring 30 remarkable mysteries from across the globe and throughout history, we arrive at a final, overarching enigma that ties them all together, a puzzle not of a single device but of a profound pattern. It is the curious case of the unexplained uniformity in ancient timekeeping systems. How is it that cultures separated by vast oceans and impassable mountain ranges, civilizations that developed in total isolation from one another according to our standard historical models, arrived at such strikingly similar solutions for measuring time. This is not about a single lost technology, but a convergence of thought that challenges our understanding of human innovation and the very threads that may have connected our ancient world. Consider the evidence laid out before us. The Maya in the sweltering Yucatan jungle and the priests of ancient India both developed incredibly sophisticated water clocks, using the steady drip of a liquid to mark the passage of hours with meticulous accuracy. On opposite sides of the planet, the builders of Stonehenge on the Salisbury Plain and the creators of the massive stone alignments at Karnak in France both looked to the moon, dedicating generations to tracking its complex 18.6-year cycle and embedding that knowledge into monumental architecture. The portable sundials of the Roman Empire, adjustable for latitude, share a conceptual kinship with the celestial navigation systems of the Polynesians, both requiring a deep understanding of spherical geometry and an ability to translate the arc of the heavens into a precise earthly location. Even the use of specific numbers holds a mysterious resonance. The 36 decans of Egypt, the 32 houses of the Polynesian star compass, the 5-day cycles on the Celtic Coligny calendar, all pointing to a human fascination with dividing the cosmos into manageable, meaningful segments. These parallels force us to confront several compelling and controversial possibilities. The first and most straightforward explanation is that of independent invention, the idea that different human minds, when faced with the same universal problems, the changing seasons, the length of the day, the need to plant crops or hold ceremonies at the right moment, will naturally arrive at similar solutions. This theory of psychic unity suggests that the human brain is wired to recognize patterns in nature, and the daily journey of the sun and the monthly cycle of the moon are the most obvious and reliable patterns available. In this view, the similarities are a testament to the shared ingenuity of humanity, a convergent evolution of technology driven by common need and observation. Yet, the sheer specificity of some similarities makes the idea of pure coincidence feel inadequate to some researchers. This has led to the more radical theory of a lost global connection, a now vanished thread of communication that wove through the ancient world. Could there have been a seafaring culture, a precursor civilization now lost to the rising seas, that carried the seeds of astronomical knowledge from one shore to another? Perhaps it was not a single advanced culture, but a slow, incremental diffusion of ideas along trade routes we are only beginning to understand. A slow-motion exchange of concepts between merchants and travelers that took place over millennia, leaving no written record but influencing the development of science everywhere it touched. The supposed isolation of the Americas, for instance, is being constantly challenged by new archaeological finds suggesting pre-Columbian transoceanic contact was far more possible than we once believed. Perhaps the most profound answer lies not in the movement of people or ideas, but in the movement of the sky itself. Maybe the greatest teacher was a single, universal curriculum written in the stars, a curriculum that every culture attended. The sun, moon, and planets behave exactly the same way whether you are in Egypt, China, or Mexico. The same mathematical principles that describe their motions are true everywhere. A society that studies the heavens long enough will inevitably discover the solar year, the lunar month, the precession of the equinoxes, and the need for intercalary days to keep their calendar in sync. They will naturally see that a 36 or 32-part division creates an elegant symmetry for calculation. The uniformity, then, is not a sign of contact, but a sign that every one of these cultures was equally brilliant at reading the same celestial textbook, independently graduating with honors in the science of time. This final mystery leaves us with a humbling and awe-inspiring thought, that our ancient ancestors in their separate worlds were all having the same brilliant conversation with the universe, and in their stones and gears and star charts, we are only just beginning to hear the echoes of their replies. From the intricate gearwork of the Antikythera Mechanism to the silent stone sentinels of Karnak, From the water-powered automata of Baghdad to the celestial symphony of the Polynesian star compass, our journey through these 30 mysteries reveals a truth that shatters simplistic narratives of the ancient past. These were not primitive people groping in the dark. They were brilliant scientists, engineers, and philosophers who looked upon the same sky we see today and decoded its rhythms with a sophistication that continues to astonish modern researchers. They tracked the slow wobble of the Earth's axis, predicted eclipses centuries in advance, and built machines that integrated time with astronomy, religion, and art in ways we are only beginning to comprehend. Each device, from the colossal to the handheld, stands as a powerful testament to a universal human drive not just to measure time, but to understand our place within the vast, orderly, and beautiful machinery of the cosmos. What truly unites these disparate cultures, separated by continents and millennia, is a breathtaking display of human ingenuity adapting to its environment. The Inca masters of stone carved an immovable solar tether high in the Andes. The Persians, living in an arid land, turned the very flow of water through their qanats into a unit of time and a system of law. The Vikings, navigating featureless oceans, may have harnessed the polarization of light to find their way. The Aboriginal Australians, in profound synergy with their land, wove the cycles of plants and animals into a sustainable, living calendar. There was no single path to this knowledge. Instead, we find a gorgeous tapestry of innovation, where each civilization applied its unique skills and worldview to the same fundamental problems, arriving at answers that were both functionally brilliant and deeply culturally significant. These mysteries collectively challenge the very linearity of historical progress. The loss of the Library of Alexandria and the ingenious devices it housed, the tantalizing enigma of artifacts like the Baghdad Battery, and the advanced mathematics of the Maya long count all suggest that the history of technology is not a simple upward-sloping line. It is a story of brilliant peaks and devastating valleys, of knowledge painstakingly gained and then tragically lost, only to be rediscovered generations or even millennia later. These ancient timekeepers remind us that intellectual achievement is fragile, dependent on cultural stability and the preservation of knowledge. Their legacy is a humbling lesson that progress is not inevitable, and that the brilliance of the past can still hold profound secrets and inspirations for our future. Ultimately, these 30 devices reveal that our ancestors saw time not as a dead, mechanical ticking, but as a living, sacred force. For the Egyptian priest, time was a cycle of rebirth marked by the Deccan stars. For the Celtic druid, it was a social rhythm etched in bronze. For the medieval monk, its measurement was an act of devotion that sanctified the day. They understood that to measure time is to attempt to grasp something fundamentally mysterious and divine. Their creations were bridges between the earthly and the celestial, tools to harmonize human life with the great cosmic order. In an age where time is often reduced to a digital number on a screen, these ancient wonders invite us to look up again, to marvel at the celestial cycles, and to remember that timekeeping is, at its heart, one of humanity's oldest and most profound conversations with the universe. We've navigated this incredible journey together, from the bottom of the Mediterranean Sea to the high Andes, from the deep past to the edge of historical understanding. But the conversation doesn't end here. I'm deeply curious to know which of these 30 mysteries captured your imagination most profoundly. Was it the bewildering complexity of the Antikythera Mechanism, a computer millennia ahead of its time? The haunting, monolithic ambition of Stonehenge's celestial alignments, or perhaps the ingenious simplicity of the Persian water clock that measured a fair share for every farmer? Share your thoughts and your favorite ancient timekeeping mystery in the comments below. Let's continue unraveling these secrets